And live. Welcome, everybody. Welcome to the Super Nerdy Friday Nerd Out about robots and whatever else comes up. Welcome in, everybody. Make sure you can hear us okay. Happy Friday. It's a little bit after 3:30 Central PM. Very, very excited and honored to have this all-star, super smart group of folks here that are in the know in robotics, AI, the future of technology in that respect. And I'm very, very excited to talk to these folks about a host of different things. But what we'll do before we even get into the topics, we'll start with Scott. Scott, give us a brief introduction. We'll go to James and then John, and then we'll get started.
Hi, I'm Scott Walter, and I've been involved in the programming of robots for probably over 35 years in the virtual world. First with a company called Douma Robotics, and most lately with a company called Visual Components. And some of you may know me from my appearances on Dr. Know-It-All.
Awesome. James, go for it.
My name is James Douma. I'm an engineer. I study neural networks. Investor, entrepreneur, currently retired and just dorking out on neural network tech. So,
oh yeah, John, go for it.
Cool. Yeah, I'll go for it. I seem to be glitching, so I hope I'm not going to lose you guys too bad.
Laggy.
But I might try Starlink anyway. Yeah. I'm actually on my cable network, so who knows? Anyway, John Gibbs, Dr. Know-It-All on YouTube, as Scott mentioned, and I teach at the University of Georgia. So go Dogs for tomorrow. There's a big football game. For those outside the nerdy realm, that's going to be a big deal. So anyway, we'll see how that goes tomorrow. It's against Tennessee.
I probably shouldn't tell you that I picked Tennessee.
So hopefully you heard me.
Maybe I shouldn't say that. I did, yeah. I picked Tennessee, actually, John. I hope that's okay. He's gonna be like, no, pick the Dogs.
Wow.
Yeah, he's quite laggy. John, you might be lagging, so maybe think about switching over to Starlink while we get started here. Okay, so John will come back. Cool. So Scott, let's kick us off. You have a few things you want to mention. You have something prepared for us here, so take us away.
Yeah, a few things, but before I do that, I was tweeting out this particular confab that we're going to have a few times, and Truth in Advertising. Yesterday I mentioned I had an anecdote that I was going to share, but it's supposed to be a funny anecdote, but I guess you'll have to judge whether it's funny. And anyway, I live about 3 hours from the Cape, so I decided to go over and watch the Falcon Heavy launch, and I was as close as the public could get, and I was like, so close that we got fogged out, and we're the only people that actually didn't get to see the launch at all. Okay, so the consolation prize was to stick around another day or two and actually watch the Starlink launch. Well, it was a Hartford launch. It was a Falcon 9 launch on Wednesday night. So I stayed there, and rather than going off at 11:30 like it was supposed to, it went off at 1:22 a.m. So I had to make the drive all the way home. I drove for an hour, went like the supercharger, a bit bleary-eyed, got out, tried to stretch and wake up, and still had 2 hours left to go. It's like, what am I going to do in the last 2 hours to keep myself awake? Oh, I know what I'll do. I'll listen to the Dave Lee interview with James Douma. And
that sounds really dangerous.
Actually, it was. I've done that drive so many times, and it's starting at 3 a.m. to 5 a.m. was the first time I was like really wide awake. So.
By the way, James, I was driving.
Were you angry the whole time at all the things I was getting wrong?
No. Unfortunately, I couldn't take notes and drive because FSD doesn't work at night for me. So I had to get my hand to the wheel.
Oh no, I was just saying. Sorry, I've switched to Starlink, so let's see if Starlink does better than Spectrum. Hey,
already.
It's an A/B comparison. Anyway, I was just saying, James, I had to go pick up my son, and so I've been watching your interview with Dave. I'm most of the way through the FSD stuff now, so it was very interesting comparing notes between what my take were for each of the notes and your take on the notes, because a lot of it we agreed, and then some of it we were like very different opinions. But sometimes they say like two-stage network, and you're like, well, what the hell does that mean? So there's an awful lot of room for speculation at that point.
Now, the first hour before I got to the supercharger, I was listening to John's notes, and I was starting to drift off. So,
oh, thank you. Okay. I see. I'm a cure for insomnia. Thank you very much.
All right, now I've got something to present. Do you have to do anything, Farzad, or am I?
Yeah. So under your screen, there's a present button. Then do share screen.
I'm just going to go ahead and share the screen, and I'm going to present this one right here. So this is the whole reason that we are having this meeting, this whole confab, and that is it's all Farzad's fault. he put out this tweet about the robots are coming, and one of the replies was right down here from the big follower, suggesting that the three of us come together and actually talk about it. And we really think it is a pretty good topic. And yeah, I was game to do it, but only under one condition, and that is Farzad, send me this T-shirt.
Boom. And just like I'm a man of my word.
Now, hopefully everyone out in the audience gets the shirt. Okay, maybe James can explain.
Look at you plugging my merch. Look at you. This is amazing. I should send everybody a free shirt.
Yes.
You absolutely should.
Okay, come on.
He's got it worked out.
Thank you so much.
Now, you gotta be careful. The last time I did a suggestion of a T-shirt like this for John, I thought it was brilliant. It was I'm on an ego trip, and it turns out nobody understands it. And
right.
it was
that would be a tough one.
It was. I mean, even people from the Tesla community didn't get it. I'm like, what? What's going on? So,
that's a pretty inside baseball joke, that one.
Yeah. I definitely love it, though. Yeah. I should have worn that one. That would have been
just
awesome.
To show off your shirt. There you go. So March the 9th.
Yeah, so there it is.
Yeah.
March the 9th, yep.
Oh, and you've got a little
paper if we ever get that many 9s.
Paper clips. It's over here. You notice it looks kind of like a 6.
Yeah.
So there you go. It's an upside down 9.
Yeah, upside down 9. Yeah. Okay. So I think I'm still sharing. Okay. Anyways, when we were talking about robots and teaching robots, usually when people ask me about robots, they think that's what I'm talking about. And no, the reality is I'm talking about the other kinds of robots, which are industrial robots. And these are the definitions. So basically, it's the ones that, let's see if this would only go, there we go. These are what I am usually thinking about when I think of a robot, an industrial robot. And the definition, there's two kind of definitions out there. The one from the RIA, which is a robot is a reprogrammable, multifunctional manipulator designed to move material parts, tools, or specialized devices through variable programmed motions for the performance of a variety of tasks. In other words, it's not really it's not single purpose, but able to do a variety of different things.
So a Roomba doesn't count? Is that what we're talking about?
Yes, a Roomba does not count, and the ISO definition makes that very clear, because an industrial robot is defined to be an automatically controlled, reprogrammable, multi-person manipulator programmable in 3 or more axes. So James, your pool vacuum does not count either. Okay.
It's an honorary robot by virtue of a science fiction story, but.
Okay. In that case, 3 or more axes, and there'll be big arguments that, well, wait a minute, the Roomba can cover 3 axes, right? Because it's got like an X, Y in a rotate. And it's like, no. In polar coordinates, it's only got 2 degrees of freedom. It really only has 2 wheels it's able to move. So it doesn't count. So there it is.
A car doesn't really count in this definition, right? Because it's only got 2 DOF, right?
Yeah, in a way. Yeah. Well, unless
I would kind of disagree with that definition then, because I think a self-driving car is a robot.
Yeah. Oh, yeah. Well, you've got to remember this is an industrial robot. So the definition of industrial robot, and trying to look at a piece of hard automation and say, is that actually an industrial robot or not? So these are the kinds of robots that I am programming and simulating on a daily basis. And they are used, of course, in factories like this to be able to do different kinds of operations by manipulating tools around and performing various processes at different locations. And the question is, how do you program them? And you program them almost the same way you have for over 30, 40 years or more. And let's see, why am I jumping to that? Oh, we'll come back to this. This was tweeted out today as the Megapack factory at Tesla, showing what they're doing. And here. For some reason, my slides are completely out of order of where I thought they were. And if I get right there, here we go. So what you see here is a teach pendant. And a teach pendant is how you actually program a robot. It has like a joystick or some kind of control in there that allows you to move the end of the robot arm over to some location and teach a location. And so it would be used to say, if you need to go to a point here, you would drive it on over until you get it there, and you would record that location, and then you would move it over to another one and teach it there. And you keep on doing it, and then you have a sequence of points you'd be able to move through, and you might have it here on a little programming page here. And that's known as online programming. You need the robot to be able to drive it around, and you need this teach pendant or something to be able to move it. And sometimes you have to get pretty close to kind of look to see whether the tip of the robot is going exactly where you want to go. It's slow and it's tedious. And that's how it was done for a while. And then In the early 80s, we started to change that by doing something called offline robot programming. And that meant we created a virtual world where you had a 3D environment of the robot that you could sort of teach the same way without using the real robot. And that allowed us to bring some CAD/CAM type of tools to make it work a little bit faster, but still you were teaching it almost the same way, one point at a time. And you had to think about what the programs were, and it was still tedious. So like one example I have is that for a welding application at Caterpillar, they were finding for every hour of cycle time, of robot actual production time, it was taking them about 100 hours to create the program online. And they wanted to reduce that. And part of it was to keep the robot in production so you didn't lose 100 hours of robot production time while you tried to teach a new part. So we brought that offline and did it in a virtual world, and this is in the late 80s. And we basically were able to reduce the amount of online touch-up down to maybe 10 hours, but they still needed about 80 hours of offline time. Okay, so it almost took the same amount of time. And all we did is we turned it from being a blue-collar job to a white-collar job. So it's not clear that we saved any money, even though we saved time. So it's kind of a one-to-one because all we're doing is duplicating what you could do in the real world in the virtual world. But in the virtual world, you could do so many more things. You can turn physics on its head and do whatever you want. You can actually identify things and say, go there and point at it, and it knows. Whereas in the real world, if I point at something, the robot has no idea what I'm talking about. So eventually we started creating more tools that allowed us to be able to teach things a lot faster by identifying features in the CAD, and then it would go ahead and start creating a lot more. And we were getting more of like a one-to-one kind of cycle time, 1 hour of programming time for 1 hour, and then reduce it even more. And that's been about the state of the art for, I don't know, 25 years or so, and we haven't progressed very much. And I'd like to see us move a lot faster. And I think the programming of Optimus is going to be not only a paradigm shift for Optimus and humanoid robots, but could also be for industrial robots. And just to give an analogy, everyone knows, they probably have one of these at home, right? Think of this as a robot. This is your teach pendant, the controller. You use this to make this go to different places, right? And then when it gets to a place that you like, you record it and say, that's a waypoint, save it. Then you move somewhere else and you save it, and you save it, and you save it, and you can have it replay that. That's exactly what online programming is. The offline programming is you take the little application that they give you in your phone and you look at a map and you start teaching it waypoints there and go boom, and then it sends it over to here, and this does that program from an offline. So that's basically the analogy of what we are doing now with the robots. And it would be nice, rather than doing that, if you just sort of describe to your drone, yeah, what I want you to do is I want you to go over that baseball field over there. I want you to hang over third base for like 30 seconds. I want you to look down at the pitcher's mound, and then I want you to do a go around and then come back to me. So, I mean, that would be a more advanced way of being able to program it.
Got it.
Those are my thoughts.
My takeaway as like somebody who's very much layman in this, but to me, it sounds like currently robots, the way we have to teach them is we have to define every single movement for them. Every movement, right? We literally, in the X, Y, Z axis, we have to literally say, this is how much you move in this direction or this vector, then this one to complete some sort of motion. And then that is repeatable, and that's what creates the efficiency.
Yeah, right? For the most part, we're really, in the very old days, they actually recorded the entire motion and played it back. And so you were recording it at a very high rate, and then you played back every single joint value to get it. And then it went to the point that, wait a minute, we just want to teach a point here and a point there, and then the controller would figure out the movement in between. You didn't have to tell it what the movement was in between. And you could change the speed, you could change the type, and you could say, is it going to be a straight line move or what they call the joint space move? Or you could teach like 3 points and say, rather than making a straight line, interpolate a circle in between them. So it could do the higher level math, but you still were kind of teaching the individual points and where they were supposed to be. And it's very tedious because you would go in and you'd figure out the speeds, but it was very visual. Unlike a lot of robot, or let's say computer programming, where you type in all this code and you run it and you just kind of see like the results, but you're not quite sure what every single line is doing. With the robot, it's very clear what each line of code is doing because you see the robot move. It goes over there and go, oh, that's what that line of code does. Then you see it doesn't move and you see, oh, there's a dwell statement for 10 seconds. Oh, I get that. And then maybe it sets some sort of output and suddenly something goes on. And then so it is very visual that way. It's very easy to play back, but it is one step at a time. It's tedious, it's slow. And when I first started doing offline programming, the group of guys that we had, when we left the university, we talked to one of our professors there, We told him what we were doing, and then he told us what he was doing. And this is 1985. We weren't quite sure what we were doing because we were kind of naive, and we were still trying to figure it out. But he was like, well, I've got a robot over here, and what I want to do is I want to put a bunch of pieces in front of the robot, some parts, and just have it put it together. They're like, oh, wow, and we were just like, you can do that? And it's kind of nagged me for the longest time. That's like, I mean, that would be absolutely incredible. And I was just assuming that like in 2 years' time, he was going to have that up, and whatever we were doing, we're done, We're nowhere near that. However, it's stuck in my mind is that's the goal. Ideally, we would like to just be able to take, some IKEA furniture and just drop it in front of a robot and say, put it together, figure it out. We humans can do it. So why can't a robot do the same thing? Now, IKEA might be taking it a bit too far, but there certainly could be applications where we put some sort of workpiece in front of a welding robot and say, just look at it and figure out where the welds are. And you figure out what type of weld needs to actually be there and just go ahead and do that. So that's more of the low-hanging fruit. And then once we get the IKEA furniture, that's artificial general intelligence right there, James. That's my definition.
That's a pretty low bar.
I don't know if that's low. I don't know.
Whoa.
Building IKEA furniture is not easy.
It's not that hard of a problem to do. The IKEA will be doable.
Okay.
I mean, if there was money in it, IKEA, there would already be people doing the IKEA furniture thing because it's super. I mean, it's not quite as repetitive, but it's a super constrained problem. It more like, give it a tree, a chainsaw, and a knife and say, make me a chair. Now you're starting to get
okay. All right. I'll agree with you there. Okay, I'll agree with you there. All right. Let's say we're on the road to AGI when it does that.
It's a baby steps, right?
Yeah.
Okay, John.
Okay, that's what I got for that right now. I mean, I have some other stuff we can jump back to along the way of some examples from industry.
I had one thing I wanted to point out about this, right?
Yeah.
Okay, leave that photo up for a second.
Yep.
If you look at industrial robots today, and I think Scott said this once before on one of his interviews with John, but in a sense, robots that get trained today, they're operating blind. They're learning a precise series of motions, and they have these very precise motors at their joints, and they have these very precise sensors that tell them the precise joint angles at every single point. So what the robot is doing is basically memorizing a set of joint positions and whatnot. Now, in order to make that work in the real world, the robot has to be extremely rigid, because if you want to be able to reliably locate like the end of that robot arm to a millimeter or less, all of the components of that robot arm have to be really, really stiff, so it doesn't vibrate, so that if there's slight variations in load or wear or whatnot, it's consistent. So that's why they're tubular, right? They're these big tubular cross sections, maximum diameter for maximum stiffness. This makes it heavy. It makes it expensive, because all your joints have to be all the joints have to be these very large cross section, extremely stiff things. So like you've got 20 bolts holding every heavy part to every other heavy part, because you've got to have this incredible stiffness. It also requires a lot of mass. But when it gets heavier, now all the motors have to be much more powerful, because the robot arm itself is really heavy.
Yes.
So that's one of the reasons that robots are so expensive today, is because they're designed to accommodate the kind of programming that Scott just explained to us. That is, it's blind programming. Now, if the robot had, for instance, cameras so that it could tell in other words, if its feedback mechanism wasn't, all my joints are at, exactly the angle they're supposed to be down to 100th of a degree, then a human being, we can do incredibly precise work, and we don't have anywhere near that level of control at our joints. And the reason that we can do that is because we take our feedback from the end point of the result. We look at, or we feel, or whatnot, what we're trying to do. And so tomorrow, if you're wearing a different wristwatch, or it's hotter outside, or whatever, like your body, you can dynamically accommodate all of these variances, because your feedback is the thing you're doing. It's not the process for how you get there. So when we're able to do that with robots, they're going to get a lot cheaper, and they're going to get a lot lighter, and they're going to be much more reliable, because because the result you're measuring is not some intermediate product. What constitutes quality on these robots is how reliably does every single joint get to exactly the angle I want it to be. If the one thing that you care about is like where the tip of the tool is at the end of the day, if that's your direct feedback and you let the robot figure out how to do it on the way to doing it, now the robot's got lots of flexibility as it gets worn, if the temperature changes, if you change the task, if the tool is a little heavier, if the work piece is a little bit different, but the mark is the same mark in a different place, the robot can just adapt.
Exactly.
So it becomes a lot more useful, and it becomes a lot cheaper and a lot more reliable simultaneously. And we get all of this stuff because now it's smart.
Yes. Yeah. Everything he just said. Okay. Absolutely. And the thing that I want to point out is there's some good examples of that in here. As James was talking, I was like spinning the mouse around, pointing out where, all the bolts are to hold it on there. Pretty much spot on. Exactly. This is something that was Sawyer Merritt found it somewhere, and I tried to find the original source. I don't know where he gets this stuff, but this was showing, and I want to go back to this example here. This is like a welding cell that they have for the Megapack. And if I stop that right there, so you see it's doing the arc welding, and the robot needs to be very stiff to get its position very accurate. But look, you also have to make sure the workpiece is exactly where it's supposed to be. So you see all these fixtures and clamps and everything, that's to make sure that the workpiece doesn't move either. And that's the only way you can run it blindly, is not only does the robot have to be stiff, but then everything in your cell has to be precisely located so that it's repeatable time and time and time again. So the cost of this cell, the most expensive thing in this cell is not the robot. Okay. Yeah. It's everything else. It's all the engineering. It's all the other stuff. So if you don't need all that, not only does it drive the cost of the robot down, it drives the cost of the entire cell down. And that's what the GigaPress did. Is it didn't get rid of the robots. It got rid of all the stuff that went around the robots. That's why it's much cheaper.
How common is it, though? Those fixtures you talked about to ensure that the product is exactly where it needs to be for the robot to do its job. How common or easy it is for that to not be the case, right? And is that what production hell is the fact that those little things that are supposed to be where they're at, they're not, and the robot just puts a weld in the wrong place, right?
Yes. And that's what happened in the early days when we went.
Right. I think. Yeah. Well, Elon talked about that specifically because I think one of the production hell things was they tried to use a robot for a flexible piece. I don't remember what it was, but some cabling or something. The fluffer body. Yeah, exactly. It was a nothing. It was those pieces of insulation, right?
You have to put the insulation up there. And, what's happening? Why is it not scaling straight?
One of the things on automotive lines right now is you can't use robots to install wiring. Right. Yeah. That's a thing where a human being's got to get in the body and climb around and, string the wiring harness through the car and do all the attachment points. And it's not like the job itself is inherently complicated, but you're dealing with this floppy thing, and robots are terrible with that. Right. It's very hard to take a flexible wiring harness and precisely locate all the points on it when you pick it up. Right. Because it's floppy. So the fluffer robot was doomed from the beginning. It's kind of amazing that they thought they were going to make that work.
Maybe this is the revenge. Maybe this is the revenge of production hell, that Elon's going to make the Tesla bots. The first job they're going to have is being to move the fluffer pieces. I don't even know if they have those anymore. I think that's kind of been obvious.
But he said later they later discovered they didn't even need it, right? And they had killed themselves over nothing. They did the best part is no part thing and designed it out.
Yeah, exactly.
Generally, but
it's still just to have Tesla bot do it.
Yeah, but it still becomes a problem, even if in the field of arc welding, that you can precisely locate the part. You've got to have the fixtures in there, but the part itself may deform and change. So in the welding world, you end up bringing like these two big heavy pieces of metal together that you hope you're locating precisely, but you never really do. And they're kind of tack welded together, and they might be thrown down on a table that you hope is positioned right. Most likely they're clamped. And so the robots always had a problem of being able to find where they were. So if you're going to be doing some sort of joint weld like this, classic sort of T-weld, and the robot's going to come in this position, what they end up doing is they first teach an air point up here, and then you go down, you go along here, and then the next time the part might be over here, and if you replay the program, you completely miss where the weld is. So they learned back in the 80s, and this is really clever. I mean, this is where the double E's are just genius. They teach the air point up here. And the first thing you do is you make sure you cut the wire on your weld so you know exactly where it is. And they would drive it down in the teach phase to see when do we get a spark. So we come down really slowly and it goes spark, and they go up, and they measure that distance. They know exactly how long it could go there. Maybe it was 20 millimeters. Then you go into production and you go ahead and it comes down here and suddenly it's 22 millimeters. Oh, we need to adjust that way. And then you do the same thing over here. You drive in that direction and find out where the wall is. So you get the base in the wall. Now I know where the joint is. But that's not the end of it, because as you're going along there, you could get some deformations. And even though you think it's a straight weld, you could stray away from it and suddenly you're not welding the joint anymore. Yeah. So what they do is that they have it weaving in there. And as you're going through there, the current varies. And from the variation of the current, they can tell whether the wall or the base is moving. And that was all done analog. And it's things like this is why I am really optimistic about the hand. Because it's like just finding silly little signals, because for a lot of people, that was just noise. But someone said, that's not noise, that's data. And if you tease out the noise, suddenly you figure out, because they couldn't do it with the cameras. You still can't do it with cameras today because the cameras get blinded by the arc. It's just too bright. And the best they could do is usually look ahead, or they use a laser or do anything else. But they did it, and you know what? They didn't add any sensors. No sensors whatsoever. You just took the existing stuff you had there, and you were just clever, and suddenly you were able to figure out this information. And it's like, you can do the same thing with a hand.
They do arc welding by feel, right?
Yeah.
You use your eyes just to get the thing in the piece, but then you can feel from the vibration of the stick and the sound, what your arc is. And you move back and forth in the space. So you're doing the same thing. You're feeling the groove and you're guiding yourself, using your hand or whatnot. It's not really an eyeball job.
Yeah. And my thought of grabbing something like this is that one of the inputs is going to be that is what the camera sees. So that the camera of Optimus is not going to be, is my hand where it's supposed to be? It's going to say, oh, that's a bottle, plastic. Oh, without a cap. This is the routine I have to do. And then I'm going to teach it another one where the cap is on, and another one where it's full, another one where it's glass, another one where it's a ball. And so one of those inputs to the neural network is just going to be, what are you looking at right now? That's it. That's it. And then there's going to be everything else, which is going to be the feedback coming from the fingers.
And I'll just throw in that in AI Day 2, the sort of POV shot that they had for Bumble C when he was watering the plants, you could see that it was semantically segmenting that out, and you could see that the watering can was colored, I can't remember, purple or something like that. Anyway, but it was definitely colored, and so it had an understanding of that as an object. So it's clearly like, pick up the watering can. It's like, well, that's the watering can. There's some flowers over there. Got to do this job. So yeah, exactly.
And I just screwed up my assumption. I thought the cap was on here. When I went to pick this up, it felt a little bit different, and then I suddenly had to change. The same thing's going to happen. It may or may not notice the cap is on there and go, whoops, oh, okay.
Yeah. I mean, that's a clever, as a human being, you reach over and you pick up a plastic water bottle.
Oh,
and
yes.
you realize
the
cap's not on because it's a little too flexible when you grab
flexible.
it.
Yes,
something
exactly.
Slightly wrong, but
something was definitely it was wrong. Yes, exactly.
Well, and that's I think that's actually an important point too, is the feedback loop. So I think about it's not an optical illusion, but a physical one, where every once in a while, like a Coke can or something, somebody's poked a hole in the bottom and it's empty, and you go to pick it up and you're like, woo, because you're like, you expect it to weigh 12 ounces. And so, you just, but the feedback loop would then immediately say like, oh, this thing's empty, so don't go so crazy. But so with whatever it is, voltage sensors or whatever, the robot will be able to very rapidly adjust if it makes a mistake at the beginning. Like if it picks it up and it's squishier than it expects it to be, it's like, oh, maybe the cap's off. Oh yeah, the cap's off. So now I should treat this differently than I had before.
There'll probably be some kind of simulation loop going on that before it grabs it, it's imagining. And that's what we do. When I go to grab something, I can already get that sense. I'm seeing in my mind what's going on. And if it doesn't match my perception, then I know, oh, I need to change. And that's exactly what Optimus would do. I'm expecting these torques, these forces right now, and when suddenly it's off, it stops immediately.
Yeah.
Right. And I'll go one step further, because actually, since I was just listening to this part before I got home, but the thing about the trajectory projection in Full Self Driving and how they totally reworked that and distilled it. to a much more rapid, light neural network as opposed to whatever this heuristic monstrosity was before. But that, for the car, it's like, where do I go? And potentially also, where do all the other cars, not the ego car, but all of the other agents in the scene, where might they be going? So there could be thousands of projections per frame for something like this. So the robot, the same sort of idea. It's like what sort of activities could I do? And it could have multiple probabilities of things to do. And if it picks up the bottle and the bottle doesn't weigh what it expects, it could then immediately jump to a trajectory. I call it trajectory, but some sort of action direct, it's not a path necessarily, but it could jump to a different, noodle. So it goes off and it goes like whoop, off to this one.
And we already have an example of that in your cars. So when you have the hatchback close, it's expecting that there's going to be a certain kind of force that's going to be applied to close that hatch. And if suddenly it encounters an obstacle, it says, whoa, wait a minute, something's going on there. And there isn't any magic sensor there that's detecting that. It's just the fact that it suddenly has to push harder than it wants and it decides to change direction.
It's a back EMF on the drive motor.
The back EMF, exactly. That's all it is. And it has no concept. And if you would say, no, there must be a position sensor on there, it's like you can actually trick your hatchback into thinking it's closed. When it's open, the light is on in the back. All you have to do is take a screwdriver and go up to the latch mechanism, stick it in there, and make it think the latch closed. And now it goes and says, oh, your hatchback is closed. It's not, it's open. So it's really not as smart as you think, yet it can do more than you could believe it could actually do.
But it's also, I thought it was interesting that they didn't talk about the sensors in Optimus. Obviously the cameras, but it looks like they're down to 3 cameras, three cameras, right? They had a single front one and 2 pillar cameras. So, but they didn't talk about like all the sensors in the hands and stuff. So maybe they just are going to use back EMF, things like that.
On the big motors, they have position force sensors. Like all the big motors that they give us details on, they had position and force sensors. And on the clutched ones, they had 2 position sensors, right, for input and output, because you can separate them. So they are. When you build your first robot, you put a lot of sensors on it. Remember Raptor 1 and Raptor 2, what they look like? So Raptor 1 is this total Christmas tree because it's got all the sensors. And then as you get stuff figured out, you can get rid of the sensors because as you polish the control systems, the sensors, a lot of them, they become redundant. So you just don't need them anymore. And, that's Optimus is going to start with a lot of sensors. And over time, he'll get rid of them. And, when we see the super high volume, million unit robot, there's a good chance that back EMF, I mean, Scott and I brought this up a couple of times, that back EMF is this, it's this multifaceted way of understanding what's going on with a motor. And all you need is to look at the current going into it, right? But it's complicated to interpret. So having a bunch of sensors that explicitly tell you, oh, this is the exact position and this is exactly how much force you're exerting right now. Like that's convenient in the beginning when you want to decouple all this stuff. But in the long run, back EMF can tell you that, and it can also tell you the temperature, and it can give you feedback like, is the robot body under vibration? There's all kinds of stuff you could potentially get out of it, but interpreting it's sort of complicated.
It's like the technical ROI. It's like the return on investment for training. Like, do we get a lot out of having this extra sensor? If no, then it's gone. So that makes sense.
And remember, it's going to be a neural net that's doing all that. If you try doing it with a heuristic, you'll never be able to tease out the data from the noise. That's why no one's really tried it before.
Yeah.
But
but they've got these neural networks that are now dealing with direct photonic input from cameras, and those have tons of noise before the ISPs get a hold of them. And, for us, like the stuff that people are watching right now, we've all been smoothed out and denoised by a bunch of stuff in hardware and software. But the original signals, that's what Tesla is, the neural networks are dealing with right now. Those things are incredibly noisy signals. So the fact that you've got a noisy signal coming from Optimus shouldn't really be a problem.
There are lots of kinds of noise. There's the electrical noise and the photonic noise. There's resistive noise. There's thermal noise that you get just from the outside temperature being different, right? But there's also the noise of it's twisted, because you can't make every single camera in every single car exactly the same. They'll be off a quarter degree, half degree, rotate. They've got all these degrees of freedom, and they'll be off. And then the lenses will be off. It'll be slightly out of focus. So the lens, because they can't be manufactured precisely the same. And so that's all noise too, that the system has to learn to essentially deal with.
Yeah, the industrial robots have the same problem. You cannot build all of them to be identical. So they go through this calibration phase where you get a signature of it. And that way the robots become interchangeable, because they used to have a problem that if a robot went down on a line, they would swap it out with another one and give it the same program, and it was missing everything. So what they had to do in order to make it accurate enough is you need to get that signature. So that's pretty much the same thing they're probably doing with the cameras, is there's a calibration phase to make sure that we know exactly what the errors are.
On the last, not on this AI day, it was on the previous AI day, they walked us through like what the camera, one of the refinements they did at a particular point. I don't know if you remember, but it used to be when you got FSD, you had to drive your car around for quite a while before it started working, because it went through this explicit calibration where it would try to figure out, well, how does my car deviate from the ideal car that the neural networks were designed for? And then later they changed the mode of doing that. They have a calibration neural network that kind of actually sits in the early stage of the camera neural network. And it's basically trained on the statistical variation of the vehicles. So like it sees a thing come in and it's like, it's supposed to be like that. And it shifts or rotates or distorts it a little bit based on what the fleet has learned about how cameras vary.
There was so along those lines, the sort of, we're talking about noise, and one of the big learning lessons from Tesla with full self-driving is that the less sensors they had, the better the system performed. So it was a big learning lesson. It seemed like when they were trying to use the radar and the sonar and God knows what other sensors they were using, there was a lot of false signal. How much of that do you think is going to be a learning lesson for Tesla Bot to really minimize how many things they put in there to ensure the system works the way it's supposed to, and it ends up shipping with really the ultimate number of sensors? In this case, it might just be cameras. I don't know, but how much of that do you expect to be part of the Tesla Bot program, where it ships with way less sensors than we would expect it to?
You want your sense modalities to expand, and you want the number of sensors you put in the thing to go down over time. So you want to get more value out of fewer sensors. And one of the things that's great about cameras is that you get so much information from cameras. They're super complicated to interpret, but they give you so much information. Like if you can figure out how to interpret that. That's what we were talking about with the back EMF thing too. It's a very simple thing, but it can tell you a lot if you're sophisticated enough about how you interpret that. The alternate, I mean, there's a valid approach to trying to do this thing where you start with the minimum number of sensors that you think you're going to need, and you use that as your design goal, and you develop your system into that minimal number of sensors. There's another approach where you put more sensors on in the beginning with the intention of taking them out as you get going. And my guess is that Tesla's going to be more along that latter end, but because my sense on all of the stuff that they develop is that they want to get something out there quickly. They want to get something working, and they want to iterate on it. So if you set the bar for your very first thing that goes out the door too high, then your team is sitting there spinning their wheels because they can't get something out in the field. If the hardware guys haven't built enough, can't get Optimus working, the software guys have to work in simulation. I mean, to make progress, you start a little heavy and then you dial down the numbers, probably, if you want to get going. That said, you don't want to start doing a bunch of things that are going to turn into crutches that are going to be hard to design out later. It's not a simple trade-off, to be sure. But you're going to start with a bit more sensors, and then you're going to try to drive them down as low as you can over time. You want sense modalities to be good. Like one big open question is like, exactly like if you want to swing a hammer, like when a human being picks up a hammer and hits a nail, there's a feel to it, and that the feedback of like hitting the nail, if you drive nails in wood, you can tell how well things are going by how that nail felt as it went. That's a super useful feedback mechanism. So do you explicitly design that into your robot? Do you just do without it? You say, the poor robot's going to be, blind or numb in its arms or something like that. It's not going to have that. Or do you find some clever way to get that information out of other sensors or other things you have to have anyway? So it's a trade-off, but the ideal is that last one. where you don't have to put an explicit sensor in there, or you've got some very simple thing you already have to monitor, and you interpret it in a sophisticated way so that you learn the thing that you need to learn. You get the feedback. But so that's why another thing when you're hitting nails is the sound matters too. Like all these things you think would matter for driving nails, but you hit very many nails, and the sound of hitting the nail, it really matters, right? Because if it doesn't sound right when you swing the hammer, you're going to look at it before you hit it again.
Got it. So then really
you don't want to be driving it through another nail, or find out that nail you're putting in is actually, it's going through a piece of conduit in the wall.
Yeah. So I guess the goal here is to solve all these things really with software, leveraging as much of the must-have things that you're building the robot with to achieve its job, and then leveraging those things as much as you can to draw the data. And if it's literally impossible, or I guess impossible shifts depending on the level of talent you have that's able to take the data that will be gathered from that event and actually using it for something else. So hitting the hammer, for example, it's visual, it's feel, it's listening. But if they can use the motors to somehow get the feedback from that hammer and use the visual to see I'm doing this correctly, theoretically, maybe they don't even need the sound, because the way it's hitting the nail, it feels like a flush motion.
Alternately, sound is cheap, right? Position sensors on motors are expensive and complicated, but sound is really, really inexpensive to do. So like sound and force feedback, some things are really inexpensive, and you might as well put them in there because they cost nothing. But sound is one of those things that's super hard to interpret. Like, how do you know what a nail is supposed to sound like, or what it's supposed to feel like when you hit it? Well, you hit some nails and you build a model in your head. If a 3-penny nail is going into a dry piece of pine, and I hit it with a 3-pound hammer, this is how it should feel. And you get it from experience, right? The fleet learns that. And then you use that model. And when it deviates from that becomes signal that goes back into the thing that tells you something about the process as you're going through it, right? So, and you can see the car and the camera decision in a similar kind of light, right? That they, or as time goes on, they're learning how to get more and more out of the cameras, and that's making the benefit that, the trade. None of these things are black and white, or few of these things are black and white. Like the cameras, you have to have the cameras. That's pretty black and white for like a car. But other things are debatable, and it comes down to like, how hard is it to get, what things work better or are easier. And, and how many more failure modes have I introduced? Like everything you put in that you rely on is another thing that can break and leave you stuck at the side of the road, right? So that's also something you have to consider.
So I want to break in here because I've got several patrons on Patreon who are European, and they are having a complete conniption fit about the lack of ultrasonic sensors, because apparently the made in Germany Model Ys now are removing those as well. And they're like, we will not be able to parallel park and do things like that because very, very tight tolerances. I mean, any kind of city where you have to do a lot of parallel parking in very narrow spaces. There is a physical optical limit of you can't see with a camera over the hood. There's a triangular.
Have you ever driven a vehicle with a long hood and had to parallel? Like humans do this.
Yeah, we do.
Yeah.
I think their concern is that they will. I don't know. Somebody puts a kid out in front of the car in a little thing, and I don't know.
All kinds of things that will mess humans up too, right?
Right.
Like there's no sensor suite. There's no set of things which makes you proof against every eventuality in the world. You have to decide where you're going to draw the line, right? So what sensors can we put into a car that are going to guarantee that nobody broke a bottle and left it underneath your tire so that when you pull away, you get a flat, right? I mean, there are things that are going to be tough. If you get the biggies and the high cost ones, then once again, it's a trade-off. Like how much complexity and inconvenience do you add, right? Because a lot of these things, like in order to add them, you're going to create restrictions on how people can use the system, right? Because you have this theory you've figured out for how to avoid this bad thing from happening, but enacting it in the world is a combination of adding hardware and software to your car and restricting the user from being able to do things like you can't reboot your car after you park it, because it has to maintain continuity of memory or things like that, where, they have a problem and they have to reboot their car and then boom, they hit the car ahead of them when they try to unparallel park. Like that's not a good outcome. It's got to be proof against all of these unlikely scenarios too.
Yeah.
Yeah.
Well, I mean, another
I-
option would be always to back up a little bit first, because that you reveal the further you can back up, the more you reveal of that space that you know.
It's
So rather than move forward to parallel park to unparallel park or something. Yeah.
one. You know, you have a backup camera and it can see
Right.
the back of your car really well. And cars are perfectly happy driving backwards. Like they drive backwards just fine. So if you only need really good perimeter understanding on one end of your car, back into the spot. The robot can back. Robots are happy. They can see in every direction at the same time. It has perfect visibility in the back of the car. Now, if you're parking in some situation, and this is hard to imagine, but maybe they do exist, where you need super precise knowledge of the front and the back of your car simultaneously.
Right.
Maybe you shouldn't park there. I don't know.
Well,
exactly.
you know,
Problem
I go back to the days before we had ultrasonic sensors, where basically what you do, you drive forward until you touch the bumper, you feel it, and then you're like, okay, time to back up now. I mean, you would hit the bumper, and
that's
work your way in. If it was really, that's New York City parking
back in the day.
So another thing, the wheel turn sensors are free. Like the wheel turn sense in the cars is really, really, really accurate. So if the car, if the car as it's approaching a spot can do a really good job of accurately mapping the space, and then using wheel turns locate itself inside that space with just a little bit of feedback from markers in the environment, right? Like, a thing humans aren't really good at is looking at a scene and knowing the curb is here and that sign, that mark on the wall up there is exactly 10 feet 4 inches tall and 3 feet 2 inches behind it, and I can use that as a beacon. Like, as long as I can see that, I know exactly where my wheels are relative to the curb, even if I can't see the curb, because as I approach that, I memorize that geometry, and now I just move inside that geometry.
Yes, I agree. It has a better position. And I've got a little bit of a theory. Can I just show my screen here again for a second?
Yeah, I got you.
You got me?
Yes, sir.
Okay, so this is something I tweeted out because I was in John's Discord, and there was this discussion about, well, if they're gone, maybe they're going to put a camera actually in a bumper or something like that. And since we don't want ultrasonics, and I kind of did this, and I thought about it a bit more. It's like, Elon really doesn't like putting holes, and of course, putting holes or putting holes on bumpers for a variety of reasons. Because first, it's not just that the sensor costs a lot of money; it's the process of putting it. It's the harnessing. The harnessing gets caught, and the things. These are the things that cause quality problems and recalls. I mean, think about for Rivian. It wasn't a design problem. It's just someone didn't torque a bolt the right amount. Tesla also had the same problem. It's these stupid little things that cause the recalls. So you don't want to have a recall because a harness came off. So they're not going to put a camera down there. It's going to be something else. And then the other thing is, if you put a camera down there, it just gets dirty. And the whole idea of having the cameras up behind the windshield is that they automatically get cleaned off every time you turn the wipers. So problem solved as far as dirt or mud or anything like that. So you want to put it in some sort of position where you're not going to have additional harnessing. So if you're going to put cameras down low, I think they're going to be in the headlights. And you're just going to piggyback off the existing harnessing and not have to do anything more if you're going to put cameras. And now this is where I take the big leap. And James, I want your opinion on this. I already talked to John about it. Could you do something with the headlights to like ping the headlights to be like a sonar, and that suddenly you see some shadows or something like that that might be cast down low that let you know there's something in front of your bumper that you can't see? Especially now that they are getting the raw data of the photons coming back.
So your idea is, because they're LEDs and there's a grid of
they
LEDs,
can control
that
it.
you could run it in some sort of pattern, so you could actually see
or something like that, and maybe even change the color or something like that. Get a certain wavelength that if you put a box in front of the bumper that you can't see, and suddenly you ping that, well, also now I'm going to see this weird shadow that's out there. And from that, I can infer someone put a box in front of my bumper.
So humans do this world model thing, right? Where you grab your doorknob when you come home, and if it's really cold or it's slimy, you notice. Like you don't have a specific sensor for doing that. You just know how it's supposed to feel. And the same thing when you park your car in your garage every night, you know what the headlight pattern on the back wall is. And if you go out there and you turn on the thing and the light pattern on the back wall is weird, then you just know something strange.
Something's wrong.
When your headlights fell out, maybe, or like it's not unreasonable to think that at some point the car. I mean, that's something you could do in the cars where they learn. You know, they're like as individuals. Like right now, all the learning is fleet learning, and to a first approximation, the cars don't have like individual knowledge that's specific to their situation they use. The few exceptions to that are like calibration related things where the cars do calibrate themselves. But it's not, you know, beyond reason that eventually you could do that, where the cars would basically their world model would get fine-tuned individually for each individual car's, you know, situation. Like, oh, you know, the neighbor always leaves the garbage can over on its side, so when I back out, give it an extra 2 feet on trash day, right? I mean, things like that you learn that the cars. I mean, it's not impossible to get them to do that at some point. And you could, at some point, that's a low-hanging fruit because everything else has been perfected. But we won't see that for quite a while.
Yeah, but it seems pretty simple that if you just have the ambient lighting, you're not going to notice that the box is in front there. But if you get something that's able to project a shadow, and that's what your headlights can do, you might suddenly notice when you ping those, the camera picks up a shadow that's not, it says, wait a minute, that shadow should not be there if there's nothing in front of me. And that might be a quick way of being able to tell whether there's an obstruction.
Yeah, it's interesting.
I'll run the experiment one of these nights, you know, and go out there, take a couple pictures. See, it's different.
The thing,
you know, it's a thing that I thought about. The cars, the headlights have really fast response time because they're LEDs. You can turn them on and off. Quickly, right? And so when when the car is driving at night, it can turn one light off and then it can like alternate the lights, right? So that the shadows that it sees of objects move in the near term, and you could use that as a depth sensor for objects that are close to the car. Like it'd be totally invisible to the human, right? Because you wouldn't notice the blinking yourself, but the car can figure it out.
Right, and they took the filters off, so you're getting all the photons of any wavelength. And so they could be potentially pinging wavelengths we don't even see.
It's fun to think about this stuff, but we're talking really blue stuff, right? Just to make it clear to the audience, we're not talking about stuff that's going to be in your car in 2 or 3 years.
It's coming out next week with FSD 1069.
Yeah. Who knows?
We've promised it now.
But you heard it here first, okay? So.
Yeah. So let me ask a question along those lines. So how unusual is it? So like the fact that we're debating this sort of thing where they could theoretically use shadows to gauge the distance away from an object because they got rid of a sensor suite that theoretically they won't need, but just in case they do, they could leverage existing sensor suites. It just becomes like a software exercise. It's somebody has to come up with the idea and then they have to sit down and sort of make it happen. So physically, it doesn't, like from a physics standpoint, it doesn't sound impossible. It's just going to be extremely difficult, and it's sort of an edge case. But how common is it for a company to go through such lengths to leverage existing quote unquote non-sensor suites that would instead be used as a sensor suite because of how it's being utilized in that use case to execute on those things? So like for me, it doesn't seem intuitive for a company to use the cameras to figure out distance of an object that it can't see by leveraging the shadows from the light as an example, right? And it seems like Tesla wants to do that as much as humanly possible. Is that unusual, or is that common, or is that just too broad of a question, impossible to answer? But is that what sets it apart, really?
So industries that operate on really thin margins and are really competitive and have highly mature products, they typically, you look at razors, and razor blades, or things that really get built in a lot of volume and they have a lot of history, and amazing amounts of effort go into simplifying those things in order. I would like the handles for those Schick razors. They're made. I learned how they were made because I was trying to use a similar kind of process for this optical thing that I was building at one point. But they're basically, you mold them out of metal, which is small, tiny metal particles mixed with a binder. You stick it in an injection mold, and you pop out this piece which is basically, it's like made out of putty, but it's in the shape of the razor. And it's like 25% larger than the actual razor is. And then you put it in an oven, you raise it to the temperature that will get all the metal bits to fuse. The particles of plastic or binder that are in there, they gradually evaporate out. The thing itself, like all of the metal bits, center together and fuse into a single piece. And it's accurate. Like you make those handles for razors, they're accurate to a micron. They're like, and they're unbelievably complicated shapes. They're just, I mean, and they cost a nickel to make, So it's like mature businesses, they do incredible things in order to get cost out and and minimize the number of things that they have to do. So they have very, very few. I don't know if this is that's a plastic one, right? I'm talking about the ones that are made out of metal.
Yeah.
Okay.
Yeah, but it, like the industrial process that's used to make some of these things, or like watch cases, right? Like, watch case, the metal, like Apple machines these things, right? And they probably have a laser machine cell or whatever the thing is that they do that. But Timex, when they make something that's, like it would be die cast, except die cast isn't accurate enough. There's this other process that you can use, which is, it's tough to set up and it's tough to get working. But once you get the process dialed, then you get these unbelievable tolerances at really low cost for these mass produced goods. So I think in those kinds of industries, like there are amazing industries out there. The way the glass is made for LEDs, TVs, they make these huge pieces of glass that they print LEDs on. And they're unbelievably consistent thickness across the thing. And the cells that make them, they make them on like a 1 second schedule. And the way they do it is they melt glass, they pour a river of glass onto this chilled metal plate. It flows out, it solidifies like that, and a robot grabs it, and then the next one slides right in. And so this robot is just stacking plates of stuff, which is made to like micron tolerance. And it has incredibly thin, the industrial processes of people do this, or like fiber optic. Fiber optic is made in spools that are, hundreds of kilometers long, and it's made on this industrial process where, they take a bowl of glass and it has these, these insets and impurities and stuff in it. And they have this rig that sits on the end of it that's got a bunch of torches, and it spins around it and precisely controls the temperature of the glass. And the glass chemistry is controlled so that it has a very precise plasticity. And they grab the tip of it with an arm and they pull. And by controlling the pressure, the temperature and the plasticity of the glass on the surface, all of the glass on that tip, it flows down. The surface tension of the glass pulls it off. And they'll just spool off 100 kilometers of optic fiber. And so that optical fiber, they'll have something which is, its diameter is like 9 microns, plus or minus like 0.1%. And it's 100 kilometers long, and it just has no defects along the whole thing. So Corning will make this stuff. They can make it for it costs them 2 cents a kilometer to make this stuff. And then they can sell it for $20 a kilometer because it's an incredibly valuable material.
I found a video of
there are lots of processes in the real world that do this kind of stuff. But typically you only get this either when you've got a company that is trying to develop an industrial process where they just completely own the space. Like there's very few companies that make the glass for, the LED front screens. There's very few companies that make optical fiber because developing the process is really expensive. But once you've got it down, you get what you're talking about, Farzad, which is people who have developed a process where they've really, so they're just going to pull that off now. Priming the machine, right? Or like the silicon wafers, they're made by, you basically take silicon, you melt it just right to the temperature where it turns solid, and then you take a single pure crystal of silicon and you dip it in the bath, and then it's just cool enough that silicon will crystallize in a monocrystal onto the end of that thing. And then you lift it out really slowly and you will form a completely defect-free silicon crystal that weighs like 800 kilograms. right? And then you precisely slice it, and that's how the wafers for silicon ICs are made.
Crazy.
Yeah, there are lots of super impressive industrial processes in the world that do this kind of stuff. Tesla, if the place you were going is Tesla unusual in its tendency to do this? I think it is actually unusual, but it's not unusual in that there are no other companies doing it. Tesla is unusual in the industries that they do it in and the complexity of the process. Like most of these other things, they're very complicated processes, need to be super precise, but in a sense, it's like a single process that you're really nailing down, right? Whereas Tesla's got like this thing they're making and it's got 25 different parts, and they're trying to do this with all the different processes that go in. And that's what I think leads you to like, why can't we cast all this sheet metal? Like, what would it take to do that? Because the giga casting, between the alloy and the scale of the casting and all the stuff that they were doing, it's a process development effort, which is comparable to, what Corning did to figure out how to do fiber optics. Like it's a really, really hard industrial process. But once you get it nailed, you've just solved the huge, like there's this thing that's fantastically valuable and would be really expensive that you can make for cheap. And you can build, that can become a cornerstone of a huge product advantage.
So the fascinating thing there is that it seems like Tesla is adopting, let's just call them manufacturing processes that are in very low margin businesses, super high volume type of industries, but they're instead doing it in an industry where for some reason it hasn't happened yet. And the reason why they have such high margins and they will in the future, it's because they're the very first one who's adopting that sort of practice in this industry. And that's why long-term, they're going to be able to quote unquote bring down prices because they already have the processes set in place for a low margin, high volume type industry. So now they can charge 30-40% margins because that's what the market wants. Right. And that's how they end up in the position that they're in.
I mean, they're very interesting. There is this observation that they're going after the woolly mammoths or the dinosaurs, right? They're going over after these big, stable things that haven't changed in 100 million years that are just lumbering along, right? And they're like, there's a lot of meat on that. All I have to do is bring it down once, right? So real. I mean, the car business it's completely full of these behemoths that have, they compete on a marketing basis. They don't compete on technology basically at all. Like technology is just this marketing gimmick that they use to like be able to charge a little more for, the car next year, which is really just a different color. And it's almost exactly the same. Or, what SpaceX did going against Boeing. It's like, try to find a more bloated, inefficient, like if you like, that's what you want as a competitor, right?
Yeah.
Like somebody who's just going to stand there while you chop them down with an axe.
Mind blowing. That's crazy. James, I know you have some videos ready for us too. Maybe this is a good time to deep dive those. So we were talking about the Tesla bot for a long, sort of the robotics rather, for a while there. We got really in depth as far as how they used to work or how they currently work. What are the sort of complexities behind it? We started talking about how software can really influence your ability to capture data where sensors are not necessarily needed, but sort of along those lines, and how certain sensors are cheap and whatever and so forth. But along the lines of Tesla bot itself, as we go into the next generation, James has some materials ready for us to go through. So I'm very excited to deep dive those. And James, if you want to give us a primer beforehand, you can, but I'll hand it over to you.
Yeah, Scott suggested this, and and he floated the tweet that started this whole thing before, like, because I do see this question quite a bit, like, how do you train Tesla bot, right? Is it just like the car? Do you just need a much bigger database? And what does that look like? And it's a great question. Because the answer is kind of yes and no. Like there are parts of Tesla bot that you can train just like the car gets trained, and they can pretty much just take FSD or the occupancy network, and they can copy it right over. And now, they can walk down a hallway with cardboard boxes instead of a street lined by trees, collect the data, and the thing is just the same. But there are lots of other things that don't work nearly as well and have to be done a different way. And one thing to keep in mind, on this stepping back is that neural networks, they're a tool that people use to design machines. it's not, you don't throw everything out and you have this neural network, and the neural network is the be all end all of the control system. Neural networks, they're a block that you can insert into a machine, and they do certain things really well. But they're expensive and complicated to do. So you tend to not use neural networks where you don't need to use them, because it's not an easy thing to start. You have to gather all this training data. You have to spend a lot of time building the architecture. They have all of these weird failure modes. It's a lot of work to get them working. But what you get out of them is there are things that you just can't do without neural networks. They're almost miraculous in their ability to do stuff that we would really like to be able to do that we just can't do any other way. And so, they're new on the scene, and they open all these new possibilities. With a robot, just like with the car, a car has 2 degrees of freedom. It's like forward, backwards, left, right. It moves on a grid of streets. It has some perception. It needs to understand its environment really well, because it's a safety critical system. You can't tolerate very many errors. Control is pretty simple. It's not trivial, but it's not super, super complicated, because you only have basically 2 degrees of freedom. You got steering and then acceleration brake at the fundamental level. But you have to understand your environment really well. So in the car, the thing you do with the neural network is you use the neural network to try to understand the situation that the car is in as well as possible. If you really understand the situation well, the rest of the problem isn't too bad. Now, there are some exceptions to that, and we're starting to see that. But the biggie was perception. Like, I've got the stuff coming into my cameras, and how do I turn that into a really good understanding of the environment that I can act in? Recently, they've started using neural networks more in planning. They've been using neural networks in planning for a little bit. So planning is like, once you know what's going on around you, planning is the process of deciding what to do about it. You've got a goal. So now you need to make a plan, and then you put the plan in action. That's your control. So we see them a little bit now. There was on AI Day 2, they showed the planning thing, where they have a pedestrian walking across the street or pretty close to the time that a car is coming down the street. And you have to decide, how are you going to handle the situation? You want to merge into traffic. You can go before or after the pedestrian, and you can go before or after the car that's coming. So you got 3 basic choices: before the pedestrian, after the pedestrian, before the car, or after the car. So this is a relatively simple example of where you've got a couple of choices and you need to figure out what's going on. Well, the planning in that situation is, well, what happens if I do each one of these things? And according to, what I care about, which is like being comfortable, being safe, being efficient, like which one scores the highest, and then you choose that. The process of going through and evaluating those different possibilities and then choosing one, that's the planning process. Now, planning with a car, once again, you got 2 degrees of freedom. So the car, when it's deciding this thing, its only real choice is like, well, what's my exact arc through traffic, and when do I start going? It's a pretty simple, right? When you get to a robot, the robot's got 28 degrees of freedom, right? So it would be, one way of thinking about it, right? If you consider that the car can make about 1 decision, 10 decisions per second, it can make about a decision every 10th of a second. If it's got, 2 choices, 2 degrees of freedom to play with, then after a second, you have roughly 1,000 different trajectories that you could have taken. Very simply speaking, this is, if you had very minimum resolution on each of these things. But if you have 28, instead of having 2 to the 10, you now have 28 to the 10 possible things. So with the robot, this brute force kind of planning, that the thing that they did, where they said, do I go in front of or behind the pedestrian? This simple Monte Carlo tree search, you can't touch that, right? Like that's a very big number, right? Like you're not gonna sit there and iterate through all the possibilities before you decide what you're going to do. You need to have intuition. You need to have a machine that kind of has a sense of, given a complicated situation, what would be roughly good ideas and what are roughly bad ideas. Now, they're already doing that a little bit. Like once again, in the pedestrian car, when do I go thing, they were showing how they build the little tree diagram. And even in that situation, the tree isn't very deep or very complicated, but you can have like imagine that you're in a parking lot and there's 4 pedestrians and 3 cars waiting, right? And you want to go to a place, but you're waiting for that guy to pull out before he goes. I mean, decisions could get pretty complicated, and forming a plan could get to be a pretty rich thing. So once the possibilities start to get pretty big, then you want to have shortcuts where there's whole classes of things you just exclude based on them being like maybe not a good idea. And neural networks are actually really good at that. You can dump a situation into a neural network. So how do you train that kind of neural network, right? Well, one way to train it is you record what humans do in all these situations, and you train a neural network. It just predicts, what would a human do here, right? Now, that doesn't necessarily give you exactly what you want, but it gives you a head start. So instead of having to do those 10 to the 14 possibilities, maybe you only have 100 you have to look at now because you've weeded out all the really terrible ones and you're down to just a few. So that's neural networks coming into planning. So another thing you can use neural networks for is modeling. So we were talking before about the thing where, when you grab your door, like if somebody left honey on your doorknob at home, like you'd notice it as soon as you touch the doorknob, even though you've maybe never touched a doorknob covered in honey before, you'd know something was wrong. Well, why do you know something's wrong there? Because one of the things that we do going through the world is we build a model of the world so that we know how things ought to feel. And when they don't feel right, you notice right away that something weird is going on. And those kinds of world models are really useful in multiple ways, not just for noticing when you've got an anomaly, but also for planning in the world. Like if I do this, what's that guy likely to do? A world model can help you do that. World models train, that's another thing which is really useful. And Tesla is starting to use world models in some of the stuff that they do in FSD right now. And we can talk a little bit about how you train those. But for the most part, world models are you look at the world and you predict what's going to happen next, right? It's an experience thing. This is what babies do. They sit in a crib, they watch stuff go around. And after a while, they know that, when the glass falls off the table, soon you're going to hear a crash, right? Mm-hmm. All of those things. And later you move to a later step, which is like you interact with the world, right? And this is the thing babies do. Like they get to be 2 and they're like, what happens if I do this? What happens if I do that, right? They're doing all these experiments because their brain is thinking about, well, what part of the possibility space have I not explored yet? Let me put that in my mouth. So they go through trying to build a more accurate model by getting as much data on stuff that they don't have as they can. So I thought as a framework, I would toss out examples of how people are solving these kinds of problems. That is how they're training neural networks to do the kind of stuff that I just listed off there. In academia, mostly in academia, because that's where most of the cutting edge stuff is. Very few people are actually doing this in robots. So this is all the stuff that Tesla is doing from an industrial standpoint with Optimus is new. Like there's no other company that's like done this that they can copy. They're going to be making a ton of this stuff up. Now that said, most of the stuff that they want to do has been pioneered by researchers who have said, well, if I wanted to do this, like how would I go about it? I'll try this kind of neural network. I'll try this kind of training data and so on. So anyway, I had a few examples of those. Sorry for the long-winded.
No, that's beautiful. That's a perfect way of framing it. Yeah, when you have it available, I'll throw it up here on the screen.
Okay, so one of the things about robots have these 28 degrees of freedom. I mean, Optimus is 28 degrees of freedom, right? A human body is like, I don't know, 250 basic degrees of freedom. And then you can probably throw in another 1,000 or something just for good measure if you include like your tongue and your eyelids and all that kind of stuff. So how do you go about figuring out how to
if you're sharing something, James, sorry, if you're sharing something and we're not seeing it.
Not sharing it yet.
Not yet. Oh, sorry. I didn't mean to, go ahead.
Yeah, I can start sharing it.
No, you're good. You're good. I wasn't sure if you needed visual aids. Yeah. Sorry.
Yeah. I'll go ahead and get started on this because it'll be easier to move between it once we, let's see, let's do a window. We want that one.
Thank you to the 491 viewers, by the way, that we have almost 500 folks on. Thank you all very much. I hope you're enjoying it. I am having a freaking blast, and I hope you are as well. All right, here we go.
Okay. So one of the things that, one way that people have gone about trying to deal with with the reality that humanoid robot bodies, or this is a quadruped, like it's basically a dog-sized robot that's got more or less basic dog type, degrees of freedom. So one really interesting possibility here is building a neural network that basically takes all the sensors that come in from the dog, and you have some simple pattern of movement that you want to achieve. And you have a neural network, and it's trained to basically cause the body to do a particular pattern of movement, given a certain set of sense modalities from the body. And it turns out this works. You can build, individual neural networks that they basically form a policy, which is given, these senses and this feel and the body in this position. What should I do next if what I want to do is walk or run or jump or step across a gap or that kind of thing? So back in 2017, people, this training robots in simulation via what's called reinforcement learning. So reinforcement learning, just to cut it short, is basically you build a simulator and you put your robot, you have your neural network control the robot body in this imaginary virtual world that you create, and you just have it try stuff. And you give it a goal, which is like walk, for instance. That might be a simple goal. Where walk is, your head is about this high off the ground and it's moving in that direction at some speed, right? Like you might define walking in those terms. And they started out with that kind of stuff, and they actually made a lot of progress. The techniques for doing this have evolved over time. This little thing is a demo of a group at ETH Zurich, who they do a lot of really fun and interesting research on using robots controlled by neural networks. And this is just kind of their demo of, this is one of the things that you can do with reinforcement learning is you can go to scale, right? There are thousands of robots in here that are all, they're sharing a single model, and they're all trying to do things in this virtual world. In this case, they're going up and down hills. They're just walking around. But because you can train thousands of them simultaneously, even though the learning process itself is pretty inefficient, you can make up for that by just running lots of them in parallel. And they've, so people out there have done this thing where they make the code really efficient and they run it on big computers, and you can train these robots. They can get, millions of years of equivalent, trial and error learning in order to figure out how to do something. So this is what they're modeling right here is, this is a simulation of an actual robot that they have. And they're trying to learn a neural network that's fairly general in terms of its ability to locomote across all of these weird terrains. The algorithm itself is pretty brute force. It's not really complicated. It just tries stuff and it sees what works and what doesn't. And it learns from experience doing that stuff. And they can get away with it because you can do this at scale. So like this is one way of trying to do locomotion training.
And so the object there that's walking would be analogous to the physical sort of thing. It's just in a virtual world. They multiply times 1,000 and then just let it learn. And then the code, like this is my layman way of thinking about it, is the code that gets generated from the optimal solution at the end, they can then stick it into physical thing, and then the physical thing should be able to walk in the real world.
Yeah, that's right.
Got it.
It's okay. Now there you've glossed over a bunch of things that like research.
No way. No, I don't believe that at all.
Than that, right? But in a nutshell, yeah, that's what's going on. Is it's refined trial and error, right? It's not trying stuff at random. It gets a sense of what kind of works and what doesn't work. And so it learns to try things that are more likely to work than not, but it's still trying lots of stuff and gradually exploring the space of all the different ways it could move its joints. So this thing starts out with no ability to move its joints at all, has no model of the world. It's just laying on the floor, flopping around randomly, right? But as it gets a goal and as it gets trained against this goal, it becomes pretty graceful and pretty capable. In fact, I've got a few videos from this group, and we'll get to see the actual robot using this thing in the real world a little bit later. But I wanted to show that like this is one approach to training. So one way that you can train for the motion control itself. Like given, Optimus wants to walk down the hallway and he wants to walk, he doesn't want to, he wants to survive catching his foot on the carpet, right? Or bumping into something. Or if he's walking down the thing and somebody bumps into him in the hall because they're not paying attention, you don't want him to go down. He needs to develop all the reflexes and stuff that are necessary to allow him to locomote reliably in the world. Because robots in the real world falling down is expensive because they break. So you want to get this down, and you do training and simulation in part because it's cheap, but also because it's really fast. Because you can have 10,000 Optimus walking down hallways, and they can all learn from their mistakes in simulation before you get around to putting it in the body. So, but this is just one way of doing it. It's not the only way of doing it. There's some things that are great to train this way, and other things don't work so well this way. And so we'll look at some other techniques too that get used.
Okay.
I think oh yeah, here we go. We'll run this a little farther. Oh, see, this is a bipedal robot here. So this is the physical robot going up some stairs. Wow. And they've taken that neural network that they trained in simulation and they've stuck it in this robot. So now this is the guy's hanging onto the robot going up the stairs because it's an expensive robot. And if it slips, he wants to catch it, right? The robot's doing the walking. He's just there to protect it if it slips. Yeah. So now it's walking over some weird objects.
And this is just with cameras, right? What are the things that they have on that robot?
Yeah, so this robot, he's got LiDAR on him, but he's actually, in this case, most of what it's doing is proprioceptive feedback. So because obviously you see, you plan where you're going to put your feet based on what you see, but the actual precision control of the motors depends on how the body moves. Right. So like when you put a foot down, you should feel a certain amount of resistance. You should move a certain way. The neural network sort of understands that, in the holistic set of all the senses that it's experiencing, mostly dynamic motion senses, like how hard should I push with each motor to keep moving in this direction, given that, maybe I'm on carpet, maybe I'm on concrete, maybe I'm walking on ball bearings, maybe I'm stepping over blocks, maybe there's a hole. It's mostly the proprioceptive feedback, and the planning comes from the vision. The vision is like, what should I do when I get to this thing? But got it. But the important part, the most significant part of this is the feedback control that the motors have that will allow it to keep going and deal with all of these strange obstacles. Got it. Makes sense. Okay, so let's look at this. Is a different robot. This is kind of a cool robot that they just started working on recently. So this one. This is a hybrid biped quadruped robot, right? And they put wheels on it because why not?
The two legs, as shown here, revolutionizes the way we categorize multi-legged robots. This humanoid quadruped transforms.
I like that it can call an elevator.
That is awesome. So this is all neural net, or is this pre-programmed too?
Yeah, so that's the thing is this is all being controlled by a neural net, which is trained to do these things.
Wow.
Right. Mm-hmm. So this is not this is the classic motion control is very different. It's all written, hand coded stuff that has dynamic models and that kind of stuff. This is ETH Zurich. They go on the complete opposite end. They're like, let's give it to a neural network and see what we can get the neural network to be able to do on its own. And over the last 5, 6, 7 years, they've been able to demonstrate really impressive capabilities. So I'm showing this off as sort of a sense of like what's actually possible in this space, and that you can hand the motion to a robot. And ETH, they do most of their training. They do a certain amount of training in the actual robots themselves. Because one of the things that happens is once you've got the robot kind of trained in simulation, you put it in a real physical body, and now it's got to deal. There are some things about the real world that aren't quite the same as in simulation. So you got to refine the model to deal with the real world things. But you don't have a million physical robots to do it with, right? And so you have this new challenge of how do we efficiently, make good use of like the, as much as we can do in simulation, and then get into the real robot and learn useful extensions and refinements with just 1 or 2 or 10 robots instead. Yeah. And they're doing that stuff. And mostly we're looking at results in these videos of what they're able to achieve using these techniques.
Got it.
So that becomes more like a few shot neural network, something that John was talking about earlier today.
Few shot.
Yeah, relatively speaking. Oh, I don't know, James, if you watched I actually did a video this morning that was related to our conversation. And the idea was that I was analogizing. It's actually a correlation. I don't think it's an analogy, but there's a correlation between GPT-3 in my mind and full self-driving, which is that you're taking a lot of unconstrained data and creating kind of a foundation model. And so what I was saying was FSD might eventually become sort of a physical analog of GPT-3 or 4, which is that it's the foundation model upon which you can build things, because like Clip, which is what OpenAI released that basically allowed things like DALL-E 2 and Stable Diffusion and other things to operate, is just a kind of reduced version of GPT. It's like it's a kind of a shrunk down. I think it's around 10 billion parameters. But anyway, the idea would be that once you've got this foundational model to create these fine-tuned things in order to create what they were doing, that which was very cool, by the way, the robot. It looked like a person on a unicycle, the way it was kind of like rocking as it balanced. Mm-hmm. But in order to do that would be a relative few shot type of learning. You wouldn't have to start from scratch. You start from where you were. Now with full self-driving, a lot of that is the sensing of the world, not the control. So I think the robot, like you're saying, is going to have to learn how to control itself in the world. Yeah, that's going to have to happen kind of from the ground up, because the car is not a good analog for it. But in terms of understanding the world, once you've got that FSD foundation model, you can take subsections of it, retrain it, do whatever you want, and you should be able to get results very, very fast compared to what people expect.
Yeah. So I think it would be the same thing. We would start to train the hand to grab this bottle in a virtual world, and we'd show it different shapes and everything else, and what the expectations can be using the physics model there. And then once you have a pretty good foundation model, now you start turning it loose in the real world, and it starts to find out, oh, that's a little bit different than what I learned. And you start adjusting those weights to get it better and better. That's when your refinement comes in. And so I think that's the idea, is that you've already got a running head start. You've got yourself 90% of the way there, or maybe 95% of the way, but it's not going to work in the real world until you get that last 5%. And that's going to be a lot easier than having to actually build a million Optimi and turn them loose in the real world. We can make as many as we want in the virtual world, but we know the virtual world's never, ever going to be perfect.
Well, but one advantage that they do have, again, is because they built out for full self-driving an amazing simulator based on the Unreal Engine, which I did not expect, but they said that was what they used. But anyway, if you've got this simulator, which not only simulates the world, but can simulate the barrel distortion and all the things that happen to cameras, and all of those kind of things are built into their simulator, so they can run a 10,000 Optimi, right? They can do this virtual thing, and it can learn how to walk in that circumstance.
But my feeling, what FSD is doing is they're doing a really realistic rendering of the world, so it looks very realistic. So the cameras
but that's
are
for the
training
cameras
on that, But the actual physics model they have is probably very basic. The physics model that you would need to model this correctly and to have a hand and come over and grab that is something very, very different.
And I mean, you've got fluid slosh and things like that.
Oh, yeah.
Just the fluid slosh alone would be really, really difficult.
Full self-driving, so don't have to worry about this problem.
And so, I'm just saying, it gives you a running head start, right? So you don't have to build 10,000 real ones.
And so that's sort of getting to that. What I think we have to do is, when we were talking about how to program Optimus, there's sort of two things that are going on there. There's skills versus tasks. So the first thing we have to do is we have to teach all these skills, and the skill will be like to walk, and then the skill of being able to walk upstairs, and then the skill to be able to start grasping things, and all those. And so you get the refinement that you've got to teach those things correctly. And now that I have the skill set, the task is very simple to say, walk over there and grab that bottle and bring it here. And so that's a different level. And of course, we see the same thing already with full self-driving, is that we don't have to teach it how to drive. We don't even have to teach it how to navigate. Our programming of full self-driving is we put in a destination. That's it. Okay. That's all the programming we as the end user have to do. And so I think that's the question a lot of people have about Optimus, is like, how are we going to program it? And I think it's the analogy is going to be very
programming
similar.
Optimus will be, Optimus, go get me a beer, right?
That's it. Exactly. And you took the word right out of mouth.
Literally what's going to be.
Yes.
It will. The
That's
goal is Optimus, the laundry's done, right?
If you hear the buzzer, time to go over and take the laundry out.
Exactly. That's all it's going to be. The question is how we kind of get from here to there. And that is going to be these discrete little things that we have to kind of teach the skill set. And then it's going to know what is the appropriate skill set I need for this, because grabbing a bottle is very different than folding laundry.
I'll let Farzad go in 1 second, but I do want to follow up on that. That again, using that analogy with GPT and Clip and DALL-E 2 and stuff, is what that enables is what we would consider human creativity. It's like you type in, give me frogs on stilts or something like that, and it produces a picture of frogs on stilts, better or worse. What will be the revealing fact is when Optimus can walk into a new house that has never been in before, and the owner says, go get me a beer. And it can go, okay, here's the house, there's the living room, there's the dining room, there's the kitchen, there's the refrigerator, open it up. If it can be creative rather than you having to show it around the house first.
Right.
If it can creatively solve a problem that it's never encountered before, that is going to be the benchmark.
They're going to be in refrigerators. Refrigerators are in kitchens. Kitchens are typically on the first floor. What floor am I at? Yeah, all those things that will break down the model. And then
and the components of that are a world model lets it predict, well, what is a house layout? Planning capabilities are, given this world model understanding of the world, like what is the efficient way to get there? And perception is looking around you to sort of understand your proximal environment, to bring in the data, to feed the world model. And then motion control is being able to control your own body and interact with things. So all of these things are potential target, and almost all these things neural networks will play a big role in. They won't play the only role. And each of these neural network bits is going to be trained kind of in a different way. Like Optimus is not going to be an end-to-end kind of thing. The ETH stuff we're looking at right now, they're just thinking about motion. They're not really one of the things you don't see here is there's a guy off camera with a remote control saying, go to the elevator, right?
Yeah.
Button, wait for the door. Like somebody's doing the planning outside. ETH is just concerning themselves with the motion control here.
Yeah. Exactly. So I think some of the thoughts that people are coming up here is like, how do you teach these humanoid robots? And you hear a lot of people out there, it's going to be done with VR, with like AR glasses or VR glasses, or we're going to do something where we inhabit it like Avatar to go around and do those motions. Or is it going to be like a teach pendant? What is actually going to be the way we're physically going to interact with it? And I think what we need to do is go down that list and sort of to say what we think about it, because I feel that you're not going to have any of those. I almost feel like VR and AR is going to be like LiDAR. It's going to be kind of a crutch to teaching. There's going to be something very, very different, and that we're no longer going to refer to a robot programmer by the term robot programmer like we do today with industrial robots. The proper term is going to be a sensei. It's going to be very simple. You go over and you demonstrate to Optimus maybe a particular skill set that you want, and it just kind of observes that and goes, what you're showing me here is like some kind of skill I already know, and maybe it's a whisking skill.
Right.
I've been taught how to whisk, and you're trying to show me how to put an omelet together, and there's something over here with breaking, and so it's going to observe that thing, figure out in its mind what that is, and maybe pick up some of the nuance in the movement that you're doing and try to repeat it to you. So it's going to be the same thing. It's like a martial arts instructor.
I was just thinking
you got it wrong. Your form is bad.
The cracking an egg lesson. I want to watch that one.
Yeah, exactly. How to do it one-handed. But that's that few shot learning. That's what we were talking about. Is you don't need a million examples of cracking an egg or whisking an egg. You just need a few. And it'll figure it out because it's got the skill set built already. So
there are some things that you want to train by getting a lot of experience in the body, right? And you can get experience in the body in simulation. You can get experience in real bodies. But it's really useful to have some basic capabilities before you send a physical body or even out. So I think you are going to see people doing the VR stuff to bootstrap it, to get some basic systems that can go out there and do useful enough stuff that they gather useful data. And as they get better at doing stuff, they'll get better at gathering useful data too at the same time. So I think we are going to see a lot of stuff in the early days of getting these systems going that won't be common, toward the end. But when we're at the Optimus go get me a beer things, and nobody's going to be using VR gloves to show it how to like.
Because you already have Connect today, where you can look at a human and you already get a model of what the human kinematics are.
Yeah.
So
I've got some videos.
Be looking at you and be seeing you move around, and it'll say, oh, hey, that's what it wants me to do. And then it translates it to itself. And that's what I'm saying. You probably won't need any sophisticated equipment, because all Optimus has to do is observe what you're doing. You go, oh, okay.
Yeah.
And it has that world model. It's the same way we do it today. We teach someone how to do something without using VR goggles. They just observe what we're doing. And then eventually it'll figure that out. So that's my take. And that's why I think you're not going to, very early on, you might have it, but it's a crutch. Long term, you're not going to be having the AR, VR goggles.
Let's see what's going on here. So this was this is the AR VR goggle thing that you were talking about, right? This is actually pretty clever. The way that they're teaching some basic manual skills, right? Like how do you manipulate certain objects, and they want to gather some data on that kind of stuff. But the thing is, if you just give the robot the bottle and whatnot, it's going to flounder for 100 years before it ever gets anything useful, because there's so many possibilities. So you start out by giving it a rough idea of these are movements of a hand inside the envelope of things that you're eventually going to be doing, and you gather data inside that space. And at the same time, it learns planning and whatnot. And the way they're doing it on this thing is, they put on VR goggles, and then the VR goggles look at their hand and how they move it, and then it moves the robot hand in that way, and they're watching the robot hand actually manipulate these various objects and whatnot. So the human user is essentially, they're remote controlling this. All they need is a VR headset. They don't even have sensors for the hands, because the cameras on the headset are looking at their hand pose and using that to control the robot. But what the neural network is doing here is it's learning to correlate what the object is doing in the camera view with what it feels with the hand and what it's doing with its hand. So this is a way of just gathering a bunch of data, which is fairly on domain fairly quickly, right? Because you can put this on anyway. They're checking out the idea. If we put goggles on a human, how useful is the data that we get from that in terms of training really basic stuff to get going? They have a few different things that they're doing here, but I just wanted to basically have something in here to show, people are doing this, and it is useful. Like, they get useful data out of this, which makes it, the data that they get is high enough quality that they don't need a lot of data to train, which is one of the downsides of having these very coarse goals. Like, if you put a robot in simulation and you give it a simulated bottle, and you give it it has no body model or no model of the world or whatsoever, and you ask it to take the screw top off of a bottle, like, it's never going to happen. It's going to take the lifetime of the universe for it to solve that problem by trial and error. But you give it a rough idea with some demonstrations, both visual demonstrations and also demonstrations like this is its hand doing this motion, like you're guiding its fingers through the movement. So it's getting that data also, right? Like what it feels like, what the range of motions that is probably useful is going to be. And so it centers on, it learns to do these kinds of motions. And then you can build on that in simulation once you've got it.
So am I thinking about it the correct way here? So as a layman, what I'm envisioning from what you guys have just discussed is that you're essentially going to have, do you remember that? Can you pull up that first video you show with like the robots walking around the crazy terrains and whatever? Maybe it's like somewhere it's still perfect.
This one
right
here.
there's perfect. So am I correct in saying that what Tesla Bot's probably going to do is there's going to be some sort of environment like this where it's going to learn how to walk correctly, how to pick something up correctly, and how to, one of the instances will be literally like a kitchen, like a random kitchen with a random fridge with a random island, just in a bunch of different permutations. And then the robot, and then the goal is get me a beer. And then it's going to try 1 trillion times through that sort of, I don't know if it's 1 trillion, but however the number is, through that simulated environment of a random kitchen. And it's going to try and find the fridge. It's just going to try to figure out how to open the fridge, and it's going to try to figure out how to get the beer. But each one of those motions of finding, locating, pulling, grabbing is going to require their own neural nets to hone those in. And then you're going to have a master neural net that's going to be able to bring all these different skills together for different tasks. Am I thinking about this correctly, or did I just massively oversimplify it?
It decomposes a little bit differently. Like you'll never do from scratch, go get me a beer simulation, because by just completely random trial and error, like flopping your joints around and whatnot, like what's it going to take for the robot? The robot has to learn to stand up, learn to perceive its environment. There are too many things. So you break the problem down. You create a perception subset, which is, let's take what comes in the cameras and turn it into something that's likely to be useful, like an occupancy map, right? So like that'll happen. In fact, Tesla's going to do that because they've already got that part, right? Then instead of it like laying on the floor and flopping its joints around, you'll develop a locomotion capability that can do useful things at a high level, like stand up, like walk, like sit down, like open a door, and that kind of stuff. And then, so a lot of those will be trained atomically, and they'll all collectively go into like a locomotion and body manipulation module. So that would be separate from perception, right? So like you build and train perception to solve that problem, and then you can build and train locomotion to solve that problem. Then there's planning. How does it take go get me a beer and turn that into like a plan for like, well, what is the goal? What does it look like?
Yep.
What would success look like? And like, what possible steps are there? And as I work my way down this tree of possibilities, I walked in the bathroom. What do I do now? Turn around, keep looking for the kitchen, right? You get to the kitchen, you open the door. There's no beer. What do I do now? You have to plan out all these possibilities. Neural networks, planning is unlikely to be entirely neural network, but neural networks can be really useful in planning. And so there will be planning neural networks, and they will be trained with some techniques that we've looked at and techniques that we haven't looked at. FSD right now is 100 different neural networks. And, a lot of them are trained in the way that has been popularized, where they go out and they take camera pictures and they just keep iterating until it knows that's a parked car and not a moving car or whatever. But there are lots of other neural networks that are doing things like, well, what would a human do here for some constrained set of inputs and outputs? And each one of these neural networks is a building block that solves a particular problem that's part of the overall system.
Got it.
Farzad, I think it's also worth pointing out, like, just to take full self-driving, because we're familiar with that. When you tell it you want to go to Target or something, the car doesn't, like, the whole planning thing, that's like a whole different stack. The moment to moment of the car.
That's a star. That's a heuristic. Right?
Yeah. I mean, so you've got Google or something else, but whatever. The robot's going to have a planning stack that'll do that. But moment to moment, the car is not thinking, I want to go to Target. It's like 1 meter ahead of me, I need to shift lanes to get over into the left lane to make a left-hand turn. It's thinking very microscopically. And so, it's like it's connecting the dots. It's like a little dot trail that it's following.
Yeah. And the go to Target thing, like, that's an important part of the overall stack, but FSD doesn't even do that. Right. They use Google searches for Target and says, here's where the nearest Target is. And if you talk to the car, it's using a speech recognition algorithm, which is not almost certainly Tesla didn't develop that. Right. So that's another, and this is going to be really important it's very likely that language model GPT, like some child of that, will be the interface that Optimus will use for hearing your voice and turning that into a concept of what it needs to do, at least in the early days. Because today, this is something that Andre talked about in that interview with Lex that we were chatting about the other day, where, he asked about embodiment, like how important is it to have a body? Well, it can be useful to have a body. Is it critical to have a body? Well, in the beginning, you're not going to have learned from having bodies. Later on, you might learn from having bodies. So you start out with your understanding of the world. You need to get it from some model. And GPT-3, for instance, is a model right now that has a certain amount of understanding of the world that it's gotten from reading the internet. It's been through all of Wikipedia. It's been through all of Twitter. It's seen all of this stuff. And so it has kind of a sense of the world. There's all kinds of things, the unwritten parts of the world it doesn't understand, right? Anything that people don't frequently write down, it's not going to know anything about. And those things it'll have to learn by being embodied. So it'll start out with GPT-3 understanding of the world as kind of a thing. Like when you say, go get me a beer or whatnot, a GPT model can actually figure that out. It knows what a beer looks like because it's got YouTube and it's got Instagram, right? It knows what a kitchen looks like. It'll have had a model. So turning, hey, go get me a beer into into a concept for a set of actions and goals, that's actually not super complicated. More complicated things, there are things that wouldn't be, that don't get written down a lot, and it'll have to, I don't know, what would be a good example of that?
I think you could take walking your dog.
Not too much starch in my shirt. Maybe that.
Yeah. or walking a dog. I mean, it can understand what the concept of walking a dog is, but leashing them, walking with them, having to deal with the fact that they pull on the leash when they see another dog that's out there, that's not written down an awful lot. That's just experiential. And that's the reason why I was actually thinking about like FSD and then the eventual Optimus version of FSD being so foundational, because it's going to be a physical experiential version of GPT. Like if it's done properly, it's going to be so broad based that you'll be able to build off of that and create lots of really cool things.
So let me use the walking your dog as an example real quick. So like if I'm just trying to like truly conceptualize what this may look like, so the robot is physically, so it's going to have a model that's going to be close enough to understanding what it actually means to go walk your dog. And it's going to pull up the leash. It's going to go outside. And then the dog's going to start pulling on the leash like my dogs do sometimes, because they're sometimes well behaved because I'm a good owner.
Mine are all bad. They're all badly behaved.
Anyway, no, I'm saying that because they pull all the time. They're like the worst walking dogs of all time. But so different dogs are going to pull at different forces, right? So the bot will know to counterbalance itself as the dog's pulling, and it's still going to continue on its task of walking the dog. But how is it going to physically learn how dogs pull? And that's where I'm like having a really hard time.
Right.
Is this the question? Is this the
just
question?
The same. Humans will do it too. Like it'll have a generalized model of its own body and forces in the world and that kind of stuff. And it'll have seen dogs on YouTube, right? I mean, there will be models. Like one of the things about that makes the embodiment the argument complicated today is lots of stuff that isn't written down is shown to us on YouTube, right? So like it'll get all that stuff kind of gets covered by the GPT thing today. But yeah, it's like, you can see people walking dogs on YouTube and you can get a general idea from that. I mean, by the time it's walking our dogs, it'll have seen lots of people walking dogs on YouTube. So it'll grok the concept, but there will still be this phase where you got to go do it. Right.
Right.
And, there will be the first person who gives their dog to Optimus, and Optimus is going to learn a lot that day. Right?
Yeah.
As it goes flat and gets pulled across the ground.
Yeah, exactly.
So that needs to happen, right?
Optimus, we're putting you in some hockey pads today.
Yeah.
So could you throw that into a model? Could you throw like a million different permutations of the bot pulling a dog that pulls differently, is a different size, walks differently, before you bring it into the real world? And how useful is that?
It'll depend on what stage of development you have gotten it to before you start having it walk dogs, right? So if it's already at the stage where it's got a pretty comprehensive world model to work from, it won't need a lot of experience with dogs to get the sense of what's going on. So I can't. Like what it takes to do training depends on kind of where you are in the arc of development of this technology. Now, Optimus, you can't do Optimus today. Right. There's a bunch of foundational stuff that has to be much, much, much more refined than it is today before Optimus is going to be able to do the stuff that we want it to do. We can see it. The thing is, by the time we get there, a lot of these technologies are going to be significantly better. So something to keep in mind is like what it's going to take to train Optimus to do the dog walking task. When we get to the point where we're asking it to do that is different from what it would take today. Today, if you start with a dog, you've got your, quadruped bicycle robot, right? And you want it to walk your dog or something like that. You got a lot of ground to cover because you haven't got any foundational models. That robot hasn't spent a million years watching YouTube, right? Like all that stuff isn't there. But by the time we're asking Optimus, to do things that require this world model, and we've given it this world model, the dog thing, it's not going to be an alien concept. Like it's going to know what a dog is generally because it's going to have seen a million hours of dog YouTube videos at that point.
Got it. That helps.
And I would imagine like, even beyond that, again, remember that you've got a hive mind here. So if just a few of these Optimus robots have walked an 80-pound dog versus a 10-pound dog, it will grok, like James was saying. It's going to grok the understanding that if this dog starts pulling, it's going to have to lean back a lot harder than a 10-pound dog, right? You know,
that's a really good point. Like Optimus is the board, right? They're not like separate minds.
Right.
Is Optimus strong enough to be able to withstand a 100-pound dog?
That's a good question.
Well, is that can a 70-pound woman walk a 100-pound dog? Right. Yeah, that's a question. Yeah. Like if a human can do it, then probably Optimus can. If a human can't, Optimus can.
Just requires leaning way back.
And will Optimus be smart enough to let go of the leash? Or will it just decide to face plant?
Be dragged.
Or be dragged or whatever,
He'll have to get out his doggy taser.
Right. Well, now I'm imagining, I want a virtual Optimus training playground where you have these virtual dogs that are just yanking every which way. The New York dog walkers that walk like 8 of them at once. I mean, that's like a PhD level right there.
I was out walking this morning. I saw a woman with 12 dogs. Like,
that's crazy.
They were amazingly well behaved too.
Well,
like, where
those are dog walkers
behaving themselves.
Yeah. It's just like you see that all the time. The dog walkers in Central Park. They just go and they keep on collecting them. They
never
go out
seen
there.
It before.
Right.
Oh yeah. There's a whole business. Someone just goes around and walks everyone's dogs during the day. Yeah. And the dogs look forward to all of their buddies. That's the greatest part of their day. It's like, they're all around there sniffing each other's butts, going around.
It's party time. It's party time.
For the dogs.
What I hope doesn't happen is the bot thinks it's like pulling a 100-pound dog, and then it's like pulling my 8-pound Chihuahua, and this thing goes flying everywhere.
We forgot. This is where
by the time it's walking dogs,
Optimus is going to learn to walk spot. That's what it's going to do first.
Oh yeah.
Oh, that would be great. Yeah. There you go.
Actually, so I'm going to show you some stuff a little bit later about mimicry, right? Like training robots by mimicking other animals. But like, it'd be interesting to train Spock on videos of well-behaved and badly behaved dogs.
Oh no!
And then you use him to train Optimus. Get 4 or 5 spots, right?
This is the fascinating part of this discussion. Is like these are like things that I take completely for granted as a human being, but walking a dog is a thing that's very that people value, like there's literally an industry built around it. And a robot theoretically the human robot has the physical ability to do it, but learning how to do it is really the fascinating part of this whole thing. But that same human or robot that's going to learn how to walk your dog is going to be the same one that's going to be in a factory building other robots. And that's the thing that's like completely blows my mind. It's
a humanoid robot. It's general purpose, right?
Nuts.
That's why we want it. There was some other cool video in this thing. It's probably worth looking at. The mobility of this particular form I thought was really interesting.
Jeez.
Like,
oh my
this
gosh,
seems really tricky.
Yeah,
it's not more complicated than walking.
But it just figures that out.
Yeah. I think it's because, we humans are used to walking, and so no big deal, but like to try to do that on a unicycle, imagine. Yeah. So we're like, wow, that's a lot harder, but you're right.
But if you had control of your own wheels, right? If those are like your toes, it wouldn't be so hard.
Yeah.
Right?
Yeah, that's crazy.
So they're talking about the technical approach that they went through to like essentially decompose these actions into things that once they got it trained, they could use as instructions that it could apply to a dependent situation.
Were they making a hive mind out of that when they were doing it in parallel?
So this one is pretty simple. They're doing it one at a time, and understand ETH's goal here is to find techniques that work. They're not trying to industrialize this thing. They're not trying to build a robot that has some particular set of capabilities. They're trying to understand what's the best way to go about training a robot, if you have a set of objectives. But it's fun to consider what its capabilities suggest about what is achievable in the near-term future.
Have you seen the stunt robot? There's a stunt robot now that does, it looks like kind of like Spider-Man. It can like fly on trapezes and do like backflips and land in nets. It's absolutely stunning. But no reason why that's any different than any of these other things.
So the original robots, the way that they got trained was you know, you put them in a simulation and you ask them to do something complicated, and then they accomplish it, but they accomplish it in some really clunky way. Let me see if I have some examples of the clunky stuff here. I don't. Okay. So we'll start with then this guy, Jason Peng, who does this research that I'm going to show you. He did a very interesting thing. As I understand it, this research started out from him trying to clean up motion capture data that's used for basically character animation for video games and movies and that kind of stuff. And he tried using motion capture by essentially, you know, you do motion capture, you put all the colored dots on people and they go in a green screen and you photograph them doing stuff, and then you turn it into Golem or whatnot after you add the special effects. But the actor is actually providing your source motion. But the motion capture instrumentation, it makes mistakes. Like, you know, it thinks you're doing one particular thing, and then it gets your elbow and your shoulder confused. And then, so now the data is all messed up.
I actually teach this stuff, and it's remarkable how bad it is.
Yeah.
And you have to do really traditional things like comb filters and butter filters, like really, nowadays it seems primitive to get rid of a lot of the noisy stuff.
Was he would take the motion control data, map a robot in sim, and then apply a physics engine so it tried to follow the motion, but it had to meet the requirements of the physics model of the simulation, and it worked brilliantly. But along the way, what he discovered is that you can teach this turns out to be a great way to rapidly teach neural network control models for robots to mimic action. So he called this deep mimic, and it's a deep neural network that was, like I said, my understanding, it was originally designed as a way to clean up motion control data, but then it turns out it's a great way for training robots, because if you have a human demonstrate some kind of motion, and then you give it to a robot in simulation where the robot has to mimic the motion, but it has to mimic the motion with the body that it has in simulation, which has mass and friction and so many degrees of freedom, but it tries to get as close as it can to the motion that got demonstrated. You get neural networks that demonstrate really amazing capabilities. And so like this one opens up, like this is a robot in sim that has learned to do, like it's mimicking motion control data, right? So, here's an example of this stuff here is if you look at how clunky these are, they just have these robots over here on the right. They just have a goal, like make your head move forward as the goal for running. And they look really clunky. But you give it a goal to like do what this person is doing. Try to move in the way this motion capture stuff is doing. And then they discovered that they could decompose these things down and actually give it goals. Like this one's trying to learn a spin kick, where it's trying to kick a particular object. On the right here, they're showing you can give it a policy, which is just like walk in that direction. And here they took the same model, and what they did is they took the same motion capture data in this. Whoops, let me move forward here a second. Take the same motion capture data from a human being and now get Atlas to do a spin kick. Well, if you take like the motion capture data of a human doing a spin kick, is like, it's going to look totally wrong on Atlas because the weight distribution and the length of the joints and everything is completely wrong. But if you do this approach, where the Atlas robot in simulation has to just do what it can do to get as close, it ends up learning a policy where, the Atlas robot here is doing a spin kick. Oh, this is kind of funny. The reason for the flying blocks is if you want to make a policy which is resistant to perturbations, what you do is you poke it while it's moving along. So it's getting these little forces, and it has to learn to maintain its balance despite the fact that it's getting hit by bricks constantly. So the bricks here are just the indicator of the forces that are being applied to it to perturb it. And they're basically showing, look, it learns to do this well enough. So this one's combining planning with motion, right? Okay, this is another great one. The motion on the right is a lion. They did motion capture on a dog, right? And then they animated a lion with it. And the other one is they took human motion capture and then they put it on a Tyrannosaurus Rex, right? And essentially what they're showing is like the motion capture doesn't have to be from exactly the body. It can be a rough guideline, and the neural network can still learn to a control policy for controlling the body to get what you need to do. So anyway, one of the things I loved about Peng's work is that he was one of the first people to show that you could get a neural network that was really graceful, that could do these really complicated. So he's going to go through a bunch of stuff here about how they do it. But mostly I wanted to show the videos from. So this is, you can see the robots having a hard time. It can be hard for robots to learn things, right? But if you give it a good
what I would
reference,
look like.
it learns a lot faster, right?
Yeah, I was actually just thinking that, these robots actually will be the best of all humans, because I can't do a backflip off the ground. But, eventually, I don't think Optimus anytime soon is going to be able to, because it doesn't have that type of dynamics. But, you'll slowly build up skills
that don't have the motion to be able to do this. But
Yeah,
we will build
yeah,
robots
exactly.
with these degrees of freedom that can do all of this stuff at some point.
Yeah,
But, once again, each of these robots, the motion control policy, which is controlling this robot's body, is a tiny neural network. Like you could, this is not something that takes a supercomputer. This is really, really, your TRS-80 could run this policy. Like it takes a lot of work to get to where it takes a lot of training to distill down the policy to this level. But the beautiful thing is that the ultimate control policy, because it is really simple, like once you get it trained up, you can have a lot of power and flexibility and grace and control. And, the training is hard, but the implementation, once you've got it, actually works super well, even on relatively simple hardware.
Whoa.
Gentlemen, I just want to point in that I promised my wife I was going to take her to dinner, so I have to leave in 5 minutes. So just FYI, but
No problem.
Okay.
you do not break promises about taking somebody out to dinner.
Yeah.
So. Anyway,
It's all good.
this
I
is
still got a lot more
fascinating stuff.
stuff.
Yeah, I know. I figured you did. I was just going to have to.
Yeah.
I'll have to tune in and watch the rest of it myself.
I think maybe there's one sort of elephant in the room that we might want to.
Don't watch it on your iPhone at dinner. She won't like that.
Yeah. Is that it was rather interesting. Was it Goldman Sachs that came out talking about the future possibilities for humanoid robots? And that was rather interesting because that's the first time I've seen the mainstream media push back against the fluxinosification of the Tesla bot.
Yeah.
You had to get that word in there. You got it.
I thought I had a stroke or something when I heard that.
No. I think James can't spell it, but I think he can explain it, right?
It's one of two 26 character words in the English language. There's a fluorescein hilopilification and anti-establishmentarianism.
Oh, there we go. Yeah, there we go. I knew anti-establishmentarianism.
We have to define it.
My excuse is
Well,
that
the
English
act of
is not my
estimating
first
something
language.
is worthless, right? So,
Yeah.
basically casting shade.
Exactly.
It's a really, really advanced way to say casting shade.
Casting shade, but I mean, in a way, it's a topic that what do we think is the potential, and it's rather interesting to see some analysts actually take it serious for once. Because when they came out talking about it, I thought, oh, they're going to just discount it and just say it's of absolutely no value. But instead, they actually gave it a potential value. So it seems like people are waking up that this is going to be a reality.
Although I have to say that the market,
on a YouTube channel thinking that this is a great idea, but it actually is something that is coming, and is coming probably a bit quicker than people think.
Yeah,
the
market share
is a little bit further away, but working in the factory, I think, is pretty soon.
Yeah. So anyway, I was just going to say that they seem to undervalue the market. They were like $10 billion. I was like, $10 billion. This is going to be way bigger than $10 billion.
154 by 2035, I think is what they said.
Yeah.
Gets
but
it should be much bigger than that. But what I'm learning from this sort of talk is that like a lot of work has been done. They've done a lot of work. There's been a lot of work out there that has been done from a simulation perspective, learning perspective, moving around, locomotion, moving your limbs and things like that, perceiving the world. It just seems like Tesla is not going to try to put it all together and make it useful.
So this is
Right.
what they did with FSD too. It's worth keeping in mind. Like most of the core techniques used in FSD, especially in the early days, were not things that Tesla was inventing. They would look at academia, they would look at other researchers who were trying interesting ideas, and they would pick ideas that were out there that seemed like they were relevant, that somebody had already done some work on. So like, it's a little bit different now. They are doing some stuff that's a little bit novel, a little bit more untried at a foundational level. But you know, the gist of the techniques that they use, for the most part, they're not inventing those. There's the AI community, the ML community, the people, deep learning researchers who are putting this stuff together. It's an incredibly fertile area. It has a lot of people exploring all kinds of ideas. So if you think there's something that you might want to try, you can go look, and you can probably find somebody who already gave it a shot, and they tried a couple of things and they figured out some stuff, and you can build on their work, right? And so that's what Tesla did in the beginning, and they're doing some stuff that is architecturally novel and whatnot, but they're not inventing stuff out of whole cloth, and they shouldn't be inventing stuff out of whole cloth because they're not in the research business. They're in the development business.
Yeah. The really cool thing is watching how fast they go from cutting edge research paper to implementing it, and you're driving it. It's like, whoa, that was not a huge time gap, you know, like a year or 6 months, a year, something like that.
There's been a bunch of times when I found out they were using some technique, and I had to go like digging through the archive to figure out where it came from, because it was new enough that I hadn't heard of it before.
That's crazy. That's incredible. But you also have the convergence of all these technologies that's making it possible. Whereas 20, 30 years ago, this was not possible. When I think about, you know, my professor back at Cornell mid 80s, you know, at that time, that was one of the resurgence of AI just before the next AI winter. And that's when they were talking about knowledge base as being sort of the term of art at that time, and that AI could do everything. And so it just wasn't ready. A lot of times people were way ahead of their time. The vision he had, I think, is valid. It's valid now. And again, just like Tony Seba keeps on talking about, the smartphone came around 2008, not because Steve Jobs was a genius, but because it's convergence of technologies that made it all possible. And Jobs was able to see that you could pull these things together.
Steve Jobs was a genius.
Steve Jobs,
that too. And he was a genius.
It's a necessary but not sufficient.
Yeah, not necessary.
Right.
Exactly.
Yeah.
So you have the fact that he's able to see it, and you see the same
I have to
thing.
go, folks. So
you better go.
Thank you so much. Yeah, I know. Believe me, I can
Get
tell
outta here.
she's mad. So it's time to go. All right, I will say goodbye, and I will watch the rest of this because I'm really interested to see where the discussion goes. So thank you so much. Ciao. See you later.
Thank you, John. Thank you for coming.
Anybody else got time limits we need to think about?
No
I
time
should
limits here.
another like 20 to 30 minutes at least from my end. So I would just keep going. Keep going.
Let's
Into a limit.
see.
For me, it's like, when is my brain gonna fry? But even when that happens, I'll just keep going anyway.
I thought some of the stuff, like, so we've talked a couple of times about pose estimation or learning from human beings. So this is more stuff in the vein of there are people actually. I'm gonna brave going to Google Live here.
We'll give you some privacy. We'll bring this up. So, can I just
topic we can bring into at one point, and that is kind of looking at AGI and specialization, the differences, because James brought that up with Dave the other day, and I think it's rather interesting. Everyone keeps on saying that, once we get Optimus going, are we going to start having specialty robots for Optimus? And that might be something that's kind of worth talking about, as in the same vein that they talked about, do you have specialty AI, or whether you're going to have AGI instead that's able to do everything?
Got it. The one thing that I'm starting to be extremely confident in this is that there is a lot of noise from areas that are like, well, this is not going to happen. There's no way. This robot thing, it's impossible. It's not. You're crazy. This is La La Land. But from watching and hearing you guys talk, it's like it's totally 100% possible. It's just a matter of putting it all together and doing it.
It's a matter of time, right? It's gonna all of this stuff, all of the components that are just fundamentally necessary for making Optimus happen, they're there. We have existence proofs for everything. Like there's all kinds of high level cognition stuff that we don't really understand. But Optimus is like, it's a humanoid shaped animal moving around in the world, right? It needs perception. It needs a basic world model. It needs the ability to plan through simple, like every single core capability that is necessary to make Optimus come together has already been demonstrated at some level. That's why it's definitely going to happen, because there's all kinds of stuff that people conflate with humanoid robots, AGI, all these other things and there's some things in those that we legitimately don't know how to do, but those things, they're not part of what Optimus needs to do in order for Optimus to like be in a factory building stuff, in order for Optimus to walk our dogs and all that kind of stuff. Like that's a lot of development. It's going to be quite a significant amount of building on stuff and building on that before Optimus is out there walking dogs. But that's totally going to happen. It's totally possible. All the core techniques, like they exist, they need a lot of refinement, but it's going to happen.
No different than the car having the cameras on the computer 5-6 years ago, and now it's on the brink of driving
just like
itself.
FSD is going to happen. It's going to
Literally
take
exactly the same
time, and it's not only is it going to eventually drive our car, eventually it's going to drive our cars so well that all the old ladies are going to want to take our keys away from all of us. Right?
Yeah.
That's the thing that's going to happen at some point, because they're going to be a lot better than we are at doing that stuff. So I had this, I wanted to show a little of this open pose stuff. So open pose, this is an open source library, which is basically what it does is it estimates human body mode. So this is a video of like people dancing around, right? So what you're seeing on this is actually, the person in this, they're comparing two different pose techniques. The reason I want to show this is I want to show that that pose estimation is basically a solved problem. So why is that interesting? This whole idea that you can take a YouTube video and you can look at it and you can figure out what the human being is doing. Like a critical part of that is how are they moving their body in space? Like what is the human in this video doing? And this is like a core, a core component of that people legitimately wondered if it was going to be possible to do it is if I shoot a video, is there an AI technique that I can use? Like, can I build a neural network that will tell me how the people in the video are moving? Like, they can find the people, can figure out how many of them there are, and it can understand how they're moving their bodies. So what this neural network is doing here is it's drawing an overlay on the people it sees, and it's showing us that it sees the segments of their body and how they're moving. Like it can map those segments as they move inside these videos. So this video itself is just comparing the performance of two different techniques. So this is the one on the left and the one on the right are two different techniques using two different code bases. The thing I wanted to illustrate is just like, this is a solved problem. Not only has it been solved, it's been solved like 10 different times. Yeah. So the pose estimation thing, like being able to have Optimus like watch a person, he's basically generating video, right? And understand what that human is doing and imitate them. So earlier I showed you that if you have motion capture of a human body, we know very well how to train robots to mimic that motion, right? That was what the deep mimic stuff was. And this is basically showing you that if you have camera video of a human being, you can turn that into motion capture. And so those are the two core techniques you need for Optimus to be able to watch a human do something and mimic it. Those are the two. Now, once again, lots and lots of refinement are necessary. These are research projects. These are not, industrial code bases that are ready to be spun out there, but they demonstrate that the techniques work. So they'll take refinement, they'll take polishing, they'll take expansion, but it's totally doable. So these are two core things. Once you've got your foundation models built and you want to program, Optimus the way Scott was saying, you go over and you do something. You put the IKEA table together, right? Hey, Optimus, watch this, right? And then it can mimic it.
Yeah. Now, this also means AI would be able to figure out intent. So if I'm looking at full self-driving and you're seeing all these pedestrians,
Yeah.
From that, you might have a better idea, is the intention of this person to actually cross
Yeah.
the road or not?
Yeah,
Or-
there's a lot of noise about, oh, how will the self-driving cars know that the pedestrian's about to step off the pavement? Yeah, that's actually not really a hard problem.
And that's the nuance.
Yeah.
And you might pick up that nuance another way, but potentially, if you go right down to the poses, you may really have an idea of what that person is intending on doing.
Well, once you have the poses, you train a neural network on the poses to predict what they're going to do next.
Yes.
You go out in the real world. I mean, you can set some video cameras on intersections where there are lots of pedestrians, and you can gather tons and tons of data and just train a neural network, predict what this pedestrian is about to do. Once you walk through that thing, you've got a little module that you can drop in FSD, and it'll be able to predict what pedestrians are going to do based on their body language as they move around.
Yes, exactly.
That's not a super hard problem. The reason nobody has explicitly gone out and solved it right now is because it's not at the top of the list right now of things that need to be solved. But when it does get there, it will be solved.
And you think that will be a pretty tiny neural net? Well, you were talking about distillation the other day, of having a very big one and then being able to get it down to its essence.
I mean, the camera nets are 1 billion parameters right now. So it won't take 1 billion parameters to do the pedestrian prediction thing from pose estimation. I mean, you know, the control policies for the robots that we were watching at, they're on the order of, 50,000 parameter size models. They're small. Like 50,000 parameters is nothing. So pedestrian prediction, there are different ways to go about doing it. The brute force way that probably people will start with is they'll train a transformer. They'll get a transformer. They'll feed it a lot of pedestrian behavior, and they'll do that. And it'll be fat because transformers are usually pretty fat. But could you make it smaller? Yeah, you could distill it down to much less. I mean, I would expect it to be on the order of millions of parameters, not billions of parameters, the pedestrian prediction thing.
Because I'm just wondering, how much headroom is left in full self-driving, that when you start solving all these things, like, okay, we want to put that in there, but is there still enough room in there? And if you're able to distill it down, then it's like, oh, it's not a problem. It's just a question of resources right now to work on that problem.
Yeah, there's going to be hardware 5, hardware 6. There's, the hardware will keep getting better. You can add more if you need to. And at AI Day 2, they spent a bunch of time telling us about how they're doing various kinds of optimization, mainly because they're trying to attract people who are good at that stuff because it's something that they want to do. Right. But they've only recently started distilling their neural networks down, and the 10.69.3 notes, they did an 80% distillation of one significant object neural network, right? And 80% improvement, that 80% reduction in size on when you distill a neural network, which distillation it's an optimization process where you take a neural network that you train and you want to make a smaller neural network that can do the same trick. Well, there's a way of transferring knowledge between neural networks. You need a bigger one to train it reasonably, because bigger ones learn faster. So you want to use a bigger neural network when you're training because it saves time. But then once you've got it, say you want to run it on really small hardware, or you want to optimize it down so it runs quicker. Well, you can do this process where you make it smaller. And typically you can reduce it 5 or 10x in size with this pretty straightforward thing and no significant degradation. Now, it's an extra process. You have to figure out how to do the distillation on this particular thing. You have to decide what the right sizes are and blah, blah, blah. It's all this work, right? But it's work. And once you do it, you've got a 5 or 10x reduction in the compute your neural network needs. And so Tesla's just barely started doing that kind of stuff because they haven't needed to. It hasn't been high on the list. But if you ask the question, like, could they do that if they needed to? Well, yeah.
So sorry, just one question there. So does that mean that you need less compute to do exactly the same task? And is it sort of like analogous to like, when you compress a file on a computer, or you zip
it? So it's exactly that. It's getting a neural network that does exactly the same thing that is 5 times smaller or 10 times smaller, and 5 times faster, 5 times less memory, 5 times less. Right.
Now, what I'm wondering is are these distilled networks something that could be distributed to anyone else, that they would become sort of open source, so that once someone cracks that thing of being able how to look at pedestrians and be able to tell what they're doing, is that something that should become proprietary, or is that something that everyone should be able to do this that is trying to do full self-driving.
The pedestrian predictor model, it'll be like GPT, that, as soon as somebody does it and decides it's useful, 10 other companies will go knock one off, and, somebody will put one on GitHub and
then everyone can start using it.
It's not going to be that hard to do. A lot of these things the obstacle is, like, once somebody does it and demonstrates an effective technique, then 10 other people do variations on it in no time. It's an interesting discussion right now. At the time, there was a window in time some years back where it was just OpenAI and DeepMind and Google research and a couple people like that. And there was all this hand wringing about, oh my God, the future of AI is going to be owned by these giant corporations. We're totally going to be at their mercy, right? And the reality has been, OpenAI went out and did GPT-3, and then 5 other people went and did their own, right? I mean, it was expensive. Like, OpenAI probably spent $5 or $10 million just training the GPT-3 the first time that they did it. But then what happened is people dug into the code and they looked at it and they found inefficiencies and they found ways to reduce the data and that kind of stuff. And, a couple of years later, people can do GPT-3 and they do it with like 10x less resources or 20x less resources. There are models out there now that, GPT-3 is 175 billion parameters. And there are people who build 6 billion parameter language models that beat it, like, on important metrics. So, most of these techniques, there's a big difference between what it looks like when the first time somebody manages to do it and what it looks like 5 years later. And at least so far, almost all this stuff gets everything that's kind of publicly well understood seems to be getting commoditized. There's 5, we were just looking at OpenPose, which is a project, and there's like 5 other human pose projects also that you can do, because it's research and that's how it works.
Dolly is kind of like that too, right? Maybe it's not a perfect example.
Dolly, Eclipse, Stable Diffusion, in a span of like a couple of months, everybody came out with their transformer, diffusion based image generation model.
Yeah. Can I just pivot over to the AGI that you and Dave were talking about the other day, or at least your discussion on that, and see if this is sort of a fair way of being able to look at AGI, and then also want to compare it with a little bit with robotics. And that is, is AGI the jack of all trades but the master of none? Because you were talking about that potentially there will always be these AIs that might be better at doing something else, like you say, for predicting the weather. Oh, did you still have me here?
That was something on my end. Never mind.
Okay, so the AGI is being sort of like the jack of all trades but master of none is one way of looking at it, or is it going to actually be not, the master of all? You gave the example that, weather forecasting, there'll still be computers that are maybe much better at being able to do weather forecasting because they're very specialized for it. We have the same problem in robotics. Is the whole idea is that, a robot is supposed to be multi-purpose and should be able to do everything. And you can come up with a robot that can do welding and can do painting and can do pick and place and palletizing, stuff like that, but it's not good at any of them. So you have these specialized robots for painting because they have a specialized wrist, or for arc welding, and ones that are much heavier and stronger for being able to do palletizing and everything else. And so even though we don't want to have the specialization in robotics, we've been forced to, because the reality is certain applications, you need a slightly different form factor for that to be able to do it. Is that going to be the case with AGI? And of course, the other thing everyone says, like, oh, with the Optimus, at some point, are we going to have an Optimus with 3 arms? Because it makes more sense to do that. Or are we going to stick with the human form factor? Are we going to have one that's 12 feet tall? Like, what's the roofing robot going to look like? Is it going to be a little bit different? And certainly Zurich is showing there that, the dogs are, your 4-legged creature can have wheels. So is Optimus going to have wheels? So these discussions keep on coming up. And what is your thought? Is the humanoid form factor going to be it? Or are we going to have all these weird variations like we have in nature, basically?
So cars mostly have 4 wheels, but we do build some that have 6. We build some vehicles that have tank treads, right? But, how many cars have 4 wheels, right? Like the humanoid form, I think it'll be the 4-wheel version of the thing. Because it's a pretty good fit for a huge number of jobs. It ends up dominating because there's an economy of scale to it, right? And so, when the economy of scale tends to like, if you can get economy of scale on a fairly general platform, you end up using it a lot for things that it's not ideal for, because the cost of building something that it is ideal for it is like 10 or 100 times more, just because you're only going to build them in small volume. And so I think that, those kind of cost dynamics are going to apply in the robot space. When there are millions of Optimi out there in the world, there will be lots and lots of non-Optimi robots in the world too, because there are going to be situations where, you're willing to pay 10 times as much to have a robot that's 50% better at this, or 20 times better, whatever. Right. So that's definitely going to be a thing. It's just that the humanoid robot is going to dominate for a certain window of time, right? At some point way down the road, when the volumes are really large, then you can afford to have, eventually you can make millions of tanks or millions of snowcats and millions of cars. Everything's got economy of scale. But there's a point in the ramping curve where the humanoid robot has got economy of scale really working for it. And very few of the specialized platforms can compete on a cost performance basis for the bulk of jobs. Yeah. Right. You've always got these outliers where a specialized thing is going to work better.
Yeah. And I don't see the industrial robots necessarily being made obsolete right away or going extinct. It's not like Optimus is going to go and take anything away from them. They have job security. Yeah. It's the humans that have to worry about it.
Nobody's going to disassemble their bottling factory and use a bunch of Optimus to.
No, they're not. And I've got kind of.
We're not going to get a union. You're telling me?
Yeah. But the programming that we learn from Optimus will translate over so that the programming of the industrial robots is done almost just as easily. That it's like just throwing the weldment down there and say weld it, and then it will figure it out.
Have Optimus program your factory robot.
That's the other, that's potentially the other way, is you could do it that way.
You have this highly specialized robot, and you've got this general one, and you use the general one to
teaching the other
as what generality you can to the optimized one.
No, I hadn't thought of it that way. That Optimus becomes the robot programmer.
Well, if Optimus is the guy who has to go in there and move the fixturing around and get everything set just right for the precision robot, and to do the trial and error and the reprogramming and that kind of stuff, then it's a general purpose labor saver. Yeah.
And I think it's sort of figuring out where's the right place, because using your bottling plant analogy, that's sort of as we look at the spectrum of where automation makes sense and everything's going on. So one example I have is, Farzad, you decided to set up Farzad's Fizzies, which is an artisanal soda shop. And you're basically, you're making 10 bottles of bespoke soda every day. Okay. Yeah. So at that point, you don't need a bottling plant or anything like that. You're just going to do it manually. So
the money's all in craft beer.
Yeah. So putting the caps on.
I don't know why Scott's pitching me this business plan here. I want to do beer.
Okay. But at some point it scales, right? And you get up to maybe you have a couple hundred. At that point, your wrist is starting to hurt. So you invest in some little simple mechanism that allows you to put it up there. It's a labor-saving device just to go ahead and put the cap on there. But you're still kind of doing it physically. But then suddenly you start ramping up and you get in around the thousands or something. And you're beginning to think, okay, can I automate this now? And it may be that's where Optimus comes in, because it can kind of take over the human task. But once you start really, really scaling up, it might be, well, Optimus isn't quite right, but does it make sense to use an industrial robot to finish that task? Or when does it make sense to put a full-scale bottling line like that?
No, it's the stuff that Tesla does on their body assembly line, use industrial robots. It's just going to work better. You want a specialized robot. Or the same thing, like the extreme example is like, look at that cell manufacturing line, right? That's not going to be humanoid robots. They're just not going to compete on that space. And industrial automation is just going to keep being like that, right?
Yes. So the bottling lines are just so fast that it has to be hard automation. And then it's when you get the smaller scales, under 1 million or under 500,000 units or so, you think about flexible automation. Where the idea of flexible automation is you get a robot that you can program to move around, because basically it's a piece of equipment you can reconfigure more easily than you can a bottling line. Because on a bottling line, if you go decide, we're going to do wide mouse right now, it's not just some little parameter you have out there on the line. Sometimes it's a whole new line you've got to come up with to do it. Whereas in flexible automation, they can very easily adapt to any changes in the product with a couple little changes. But they may not be,
integrated circuit pick and place machines or IC PCB fabs. Like they're a great example of super high volume, super low cost, flexible manufacturing. Those pick and place machines, you know, they put down 100 components a second or something like that.
Oh, they're unbelievable. I think you look at that; it's unbelievable how fast they are and how precise.
What are they
Or
called
like
again?
a wire
What are
bonding
these called?
machine that like you literally cannot see wire bonding machines. They move.
Oh yeah, and the other thing is the way that they actually have to feed the components. You'd think they have a stack of them. They have a tape. It's almost like a machine gun belt where these things are just running through. Yeah. They're going to keep on grabbing them off as quickly as possible.
Where Elon was saying he was what was it? He was speculating about like at what point they're going to evacuate the factories because the air resistance is the limitation on how fast they can make stuff. I like that. That's great thinking.
Yeah.
I think you know that might be a little way out. That's Alien Dreadnought 3.0 or something. At that point.
Yeah.
But in that industrial robot sort of like world, so like say take Tesla's factory line today, there's still a lot of processes within that line that is humans, right? So the humans are general assembly somewhere in the middle. So I think it also stands to reason that if you do have this like sort of like marrying, right now it's man and machine, but it's like humanoid robot and machine that's going to be married. I feel like that implementation of the bot in those processes, as long as it doesn't make sense to have an industrial robot doing that task, you're probably going to make the industrial process, that industrial robot, more efficient because now you don't have human error that's clogging up that process, right? Because that's usually why these manufacturing processes take a while, is because you're trying to work through the human error. You're trying to work through, okay, so like put it in here, it's messed up, you know? So that in itself is going to make the industrial robots faster just by having humanoid robots in. So you go from like, 0.02% error rate, which means X number of units per year, to basically zero. Because I don't think robots make mistakes unless they fail, unless they break, right? So
well, there's always stuff outside your training distribution that you encounter, right? And then you turn the data engine again and your error rate goes down. Yeah. But if Optimus can do the wiring harnesses in the car, if he can deal with the floppy stuff, then you've got a category of job now that you can automate that you couldn't before.
Yeah, and you're also thinking about the rates that you're going to have of how quickly the humans are able to do a particular part assembly before they're feeding something to the robot. And that is not something that they're allowed to go to 100%. They work out the ergonomics on it, and the utilization of the human is supposed to be 85%. So whatever the cycle time is that you've set up for that cell, you've got to make sure the human can do whatever the preloading task is at only at 85%. So they have a little bit of a break in between and also a little bit of variance. So now if you can get that down, that we can get 100% utilization, that changes everything. That changes the calculation. Yeah.
Fascinating stuff.
So I'm out of stuff.
Okay.
How are you guys doing on time? You have anything else you want to talk about?
It's up to you guys. Yeah, I mean, I don't have anything to bring up. I think I'm reaching the limits of like my brain being able to absorb information. I don't know how you guys feel. I know James can go for 10 hours straight here.
Yeah, and actually, I've got the weekend to rest up because round 2 is Monday night, right, James?
That's sad.
Monday night, you're on Alien Space with me.
That's Friday?
No, that's the 7th. That's Monday, isn't it?
Is it Monday? Oh man,
the 7th. I'm thinking the 7th. It's Monday. Today's Friday.
Be double booked. I'll have to go.
It's Friday right now. Okay.
Today is Friday.
Today is Friday.
Yeah. No. Yeah. There's more stuff coming. It's true. I've not been released yet.
Yes. Yeah. Okay. But that's gonna be something different. We're not gonna probably talk so much about Optimus and FSD, but give you a chance to talk about something different for once.
That's awesome.
Space.
Yeah.
Space related stuff. Yes. Exactly.
Make sure you go check that out. Alien in Space, great channel. Monday, what time? What time are you guys going on? Do you remember?
I don't. Apparently, I don't remember.
I think. Yeah, she has it up. I have to go ahead and check my calendar right here to make sure I have it.
If I can pull it up.
I think it's going to be. Yes, it is at 7:30. 7:30 Eastern time.
There you go.
7:30 Eastern.
It says 7 o'clock Central for me, so maybe it got changed to 8 Eastern.
Okay.
But
do I have it down wrong? Oh, it's 8. It's 8. No. I put it in my calendar at 7:30 to make sure I'm here. Okay, it's 8 o'clock. There we go.
We'll give her a like. We'll give her the plug.
It's at 8 o'clock. It's at 8 o'clock Eastern. Yep.
Perfect.
Yep.
Oops, we got big there. But yeah, make sure you go check that out Monday.
Yep.
Thank you, gentlemen. My goodness, that was very eye-opening for me, because one of the things that was in the back of my head was I've always felt confident that Tesla and the team, when they put out a grand vision, they execute against that grand vision. And for me, the reason why I found the opportunity in the very beginning, 10 years ago, when I started investing in the company, because I understood what it meant when you have an electric vehicle that's going to change the way we move around, and then self-driving, I got to actually experience it. I'm like, oh, holy crap, I get it. But the humanoid robot, I was going from a trust perspective. I was going like, well, I trust them because they have a track record of execution. And this is why I think they're going to get the bot done. After today's discussion, I'm like, okay, everything's there already. You just got to put it together. It's hard as hell, obviously. It's not like anybody can sit down and do it. But they have the talent and the problem-solving skills, and they have the leader and the culture to do it. So why wouldn't they do it? So for me, it's solidified that much, much better. And I think I'm so excited to see the very first version of it, like the actual, like, the first one that gets sold to somebody and they can use it in a place. Like the second I can go to Tesla.com and buy it. I'm buying it. And I'm going to do every single one of my podcasts with Tesla Bot. It's going to be right here, right next to me, wherever it is. We're going to have a grand old conversation about itself, and it's going to be incredible. And maybe the universe will fold onto itself. It's going to be amazing, But
optimistic will get me a beer. Yeah,
that's right. I'm going to be so drunk by the end of it.
Yeah.
But no, seriously, thank you, gentlemen. Yeah.
You're welcome. So I think this whole thing about Optimus, I agree. It's so easy to be sucked in by people who like to do the fluxinasi-nihilification of it, and just don't let them fluxinasi-nihilificate Tesla Bot too much. And it's going to happen. It definitely is going to happen. And I think sooner than people.
I mean, it's easy to kind of have this dialogue be misunderstood as it's going to happen quickly, or it's going to not be bumpy. It's going to be bumpy. It's going to take a while. It's just a lot of work. I mean, Starship, right? Like, it's, we had hopes that we were going to see it fly a few years ago. It's a hard problem doing that kind of stuff. But, Starship was a physics problem, right? You got this metal, you got these rockets, you got to get this stuff together. It's very complicated. There's all of this control stuff and whatnot. But at some point, the guys working on it, they just know it's going to work because they can see the path. Or when we hear, when we hear the battery guys talk about the battery line at Tesla, it's like, it's not there yet, but we see the path. We understand the stuff that the big questions, they've been answered, and now we just turn the crank and we get there. And Optimus is like a big version of that. Optimus is like Starship, right? It's a 10-year thing, right? It's just going to take a while from the time you get going to where you're showing real results. And there'll be useful, cool things along the way. It won't. I mean, it's not like nothing, and then 10 years from now you have everything. That was one of the big misunderstandings about FSD, which I think Elon has not contributed positively to this idea that it's going to be a road and there's going to be intermediate stuff that we're going to get there. Because certainly a lot of the initial dialogue about it was just like, the fleet's going to wake up, right? And suddenly, we're going to go from no robot cars to no robotaxis to 1 million. Like that was never in the cards. And we're now, but now we've seen it happen once. Like FSD is going to be a great sort of, touchstone for us to understand how these other kinds of grand vision, complicated developments with intermediate products are going to unfold. And Optimus will be one of those.
Yeah, and I agree. And I think Andre kind of brought that along by saying that it's going to be these little steps and the dopamine hits that you get along the way. It's going to start out easy. It's going to have some sort of benefits immediately to Tesla. That's the big advantage that Tesla has, is that they can find some utility right away. I think I saw someone put out their tweet that they thought Optimus was going to be doing the roofing right away because Elon had said something and they put it into context.
That's a Warren, right?
I don't know if it was Warren or someone else, but the thought that it was going to pretty quickly be doing the roofs, and I don't think so. I think that's still a ways away. What's your opinion on that? It was kind of a question. Was going to be soon, and what does soon mean? And
well, for people who think it's never going to happen, ever is soon. So
Right.
You know, there are things that take 10 years to do. And
Mhm.
there's also this question about how well it does it. Like, you know, if Optimus can do anything on a roof, like at what point are we there? When
Yeah.
Optimus can totally make it so no human ever has to get on a roof, well, that might be a
Yeah.
little later, right?
Yes.
But yeah, you know, making making predictions is really tough, especially about the future.
Yeah.
I'm an optimist. I've been wrong about pacing on a bunch of things. I generally
Yeah.
expect stuff to happen faster. And I'm an optimist, and I like it
Yep.
that way. I'm not going to change. But that, you know, realistically, it's a 5-10 year thing, right?
Yes.
To get this
Yeah.
stuff happening.
Yeah.
It's
I
not
think,
a 2-year thing.
actually, I think it was Big Follower who put that out and said something like, you know, Tesla bot will soon assist humans, solar roof installers. Elon said installation cost is still way too high right now. It's like, yeah, we all agree it's way too high. And I think it will eventually, but, you know, not within the next 2 years.
But
It's gonna be
eventually
factories
here
first.
doesn't mean 50 years. Eventually
Yes.
means, you know, 7 years, right?
Yeah. I think so. By the end of the decade, probably, but it'd be quite optimistic to be before that.
Yeah.
One thing that confounds this stuff too is that if you have a full press, like if you decide there's this application that you really want to happen and you're going to put it at the top of the list and you're going to make it happen soon, you can pull in that date a lot because you can compromise on a lot of the stuff that goes into it.
Sure.
But if we're talking about, you know, the date when a roofing Optimus just with a general capability comes off the line and you're the first guy, he shows up at your house and you dig out the solar panels and say, Optimus solar panels, right?
Yeah.
Like that's farther down the road for it to develop, because in the second case, it needs, the generality will improve over time, and the less general it is, the more work it is to get it to do any given thing. And over time, as its generality improves, you can do more with it with less effort. So there'll always be the first time, hey, look, I got Optimus to do a backflip, right?
Right.
You do a lot of work and a bunch of training and all this kind of stuff, and you got it to do a backflip or something. But then there'll be the day when it can do complicated things that just by being instructed without ever having any practice.
And it could be that it assists and doesn't do the whole thing. Because if you think of what's involved, there's a lot. Stripping the original roof that might be there, putting up the frame, laying everything down, putting it up. So it's going to be an apprentice. Right? And so the intermediate stage might be bringing things up a ladder, or, once something has been prepped, Optimus can go in and just start clicking them in and then start snapping all the things together. And if there's some drilling or riveting, that's a very simple gun. It's just,
but that's a pretty good example of something that's actually pretty hard to do, right? I mean, it's not a coincidence that they're having a hard time getting productivity up, because roofers will tell you
it's hard.
There's all these corner cases, like literally the corners on the roof.
Corners, yes, yeah.
And
they're compound corners, which is the big problem.
You see all this weird stuff, that you've never seen before, you hadn't had to deal with before, or something that's broken and got repaired in a weird way or whatever, right? It's like auto mechanics, right? It's like, in theory, you turn a bolt and it comes off, but anybody who's worked on an old car knows that you turn a bolt and the head breaks off.
Head breaks off. I know that.
The gun, right?
Yeah, exactly. It starts over.
So it's one thing to deal with the clean system where everything is working, and it's something else to deal with the real world.
Mm-hmm. Yeah. So if it's a new build, it'll probably be easy. And again, it's got to be like in the operating room, the surgeon goes in and does all the interesting stuff. And once they're done, they say, nurse, close, and then someone else has to come in and actually do the final part of the surgery. And it might be like that with Optimus.
Robot already.
Yeah.
That does complicated surgeries really fast.
Yeah.
And I had a friend who he had to have something removed from a kidney, and apparently for a human being, it's like a really complicated operation, because apparently when you cut tissue off of a kidney, it really bleeds. And so they have to do all this prep work and set everything up. And they have the Da Vinci robot. It's like, it's arthroscopic, but it has 7 different incisions. So they stick a bunch of cameras and they pre-position everything. And then once they've got, all the stuff set, they flip a switch and it does the surgery in like 10 minutes. Right.
Yeah.
So it ends up being much less traumatic and whatnot.
Yeah. Da Vinci is pretty scary looking. There's no doubt about it. Because if you go to the operating room and you see that thing next to you, it looks like something out of Alien. It's like all these arms are all over the place. You want to know what's going on. And when I've looked at the kinematics of that thing, I don't know what they thought of and why it is set up the way it is, but it seems to do the job.
Yeah, it's suturing a grape here, right?
Yep.
Yeah. Crazy.
So this is the simple version of it, which is just these are Waldos that a human being is using, right? And they're just demonstrating the dexterity that they can get with a couple of Waldos. But there are versions of it where you pre-program it. You set it up and you pre-program a set of movements, and then once you do all the prep work, you flip a switch, and then it sort of automatically does a sequence of preset actions very quickly.
Wow.
Yeah, and there's also a company right by you, Farzad, Monogram Orthopedics, which is doing a similar kind of thing, where they're having to go in, and the thing is your environment is different every time. The human, it's similar, but they're all unique. So the first thing you need is good data. So you have to go in and get a really good scan of the bone to be able to go in to figure out exactly where the operation has to be done, how you're going to perform it. And also remember the fact that the human is very flexible, and sometimes there is movement occurring no matter how much you try to do to hold someone down. So you have to real time be able to figure out where your bone is as you're doing the operation.
The anesthetic again.
Yeah, exactly. And it's pretty cool.
Won't stop moving around.
Oh yeah, no, it's really interesting what they do, because they have a bunch of landmarks that they're able to go through and from the bone figure out what it is, and then they insert a couple of basically tooling balls. And once they have those tooling balls, now they know exactly where it is. And then they have a KUKA robot come in and mill out the intermedullary canal perfectly to be able to fit the orthopedic insert. And that's something that's very difficult for a surgeon to do. Normally they just go in and they just ream it out, and then you get it and you hope it's about the right size, and you have to put a bunch of epoxy.
Use a lot of glue to fill the gap.
Yeah, in this case, it's exactly machined out to what the orthopedic implant's going to look like, and they just pop it on in the right orientation position, and that is actually, instead of epoxy, the bone grows into the prosthetic, so you get much better results. And that can only be done because it's precision of the robot, and because real time you can track what's going on. That's the real trick, is the calibration that's going on with it.
Wow, that's really interesting. I didn't know they were using a KUKA robot to do that stuff.
Yeah, they're using the Iowa robot, the 7-axis arm, which makes sense because you want to make sure you don't have a position where the elbow is suddenly bumping into something. If the elbow is in the wrong way for the arm, you can relax it and bring it around. And it has enough precision to be able to pull off that trick.
Oh, cool. That's really interesting.
Yeah, so
must be fun.
Worth checking out. They're right near you. Next time you're in Austin, we all have to go together.
Let's do it. I have a message behind me. The robots are coming. It sounds like the robots are here already. From the sounds of it, we have a lot of robots out there.
Yes, they are.
A lot of incredible things.
Yeah,
incredible. Thank you all so much. Let me plug your guys' Twitter real quick here before we head out. Scott Walter, PhD, going ballistic 5.
That's pronounced FUD. Okay, just so everyone knows, PhD is pronounced FUD.
FUD.
Yes.
There you go. He's got a piece of paper that's paid for to just spread FUD. Nice.
Yes, exactly.
And our friend James Douma at Jimmy. Perfect. Yeah. I love the profile thing. Anything else y'all want to plug before we head out here? Anything else people should be looking out from you guys? No?
Nope.
Good. All right. Thank you, guys. Thank you, everybody. Sorry. Go ahead, James. Sorry.
Go ahead.
Yeah. No, you're welcome.
Sorry. Maybe I'll plug one thing. Just the robots are coming. Merch line in the description below. That's from the store too. James, I'm going to send you a free shirt.
Okay. This is number one. Yep.
That's the one of one right there. Yeah.
Yep.
Actually, let me bring this one here. Let me just show it real quick. Yeah, this is like all inspired. Like this is the stuff that really fascinates me. So literally my merch is all themed around the coming age of robots, and so awesome. It's the robots are coming. Check it out. Cool. This has a design on the back too. A robot generated by DALL-E. So I literally typed like a prompt.
Wow.
Yeah. So I'm already like finding a use case for DALL-E. So it's like fascinating.
Did DALL-E do this one? No.
Definitely. I typed March of Nines and that came up.
Came up. What happened to your original March of Nines? You actually had the 9s that were marching down?
Oh yeah, I still have that. Yeah, it's actually on the secret store. Yeah. I have like a secret store for folks that support like the channel or whatever they have access to. And so what I'm doing is like I'm trying to conceptualize, like my dogs are going crazy in the background. They're like, we don't want to be walked by humanoid robots. That's what they're saying.
They will once you give the robot all the bag of treats, right?
That's right. Hell yeah. Hell yeah. I want to get the beer. They're going to get the treats. Everybody's happy. What else do we need?
Yeah, right. Train the robot to train the dogs. This is gonna be fun.
Yeah. But yeah, thank you guys very much. We'll see you around in the comments. Make sure you go check out Ellie's channel on Monday, 8 o'clock Eastern, 7 o'clock Central for these two gentlemen on her channel. And yeah, let's do this as often as y'all like. I'd love talking to you guys. I'm sure as we go through the bots evolution as the months and weeks go by, it's going to feel like. I'm open to having a forum discussion once again, and I think the folks in the comment section really appreciated it as well. So thank you both. We'll see you around. Have a great weekend, everybody. We're going to end the broadcast. Take it easy, y'all. Here we go.
Bye.